In this video, I'm going to help you grasp a basic idea of what Apache Cassandra is and give you a quick tour of its project website. You may not know how and where to get started in Cassandra. I'll introduce Cassandra briefly so you'll have the foundation for the following lessons. Please note that this training is geared towards Cassandra version 1.2.3. First, some definitions. Cassandra is a non-relational database, also known as a NoSQL database, designed to operate in a distributed environment or cloud infrastructure. NoSQL databases, also known as not only SQL, generally refer to any database system that doesn't use structured query language, SQL, as its query language, providing a mechanism for storage and retrieval of data that employs less constrained consistency models than traditional relational database. Cassandra is scalable, elastic, performant, and fault-tolerant, and is therefore very suitable for a large volume of mission-critical data, depending on what hardware configuration you're giving to it. It's a combination of Amazon's Dynamo and Google's Bigtable to provide a column family-based data model. It was donated to the Apache Software Foundation by Facebook in 2008. It's being used in production systems by Netflix, Twitter, eBay, Cisco, and many others. The largest known cluster is formed with over 400 commodity machines managing over 300 terabytes of data. Okay, let's have a look at its official project website. The project website is under Apache Software Foundation and can be found at cassandra.apache.org. Let's go. The homepage comes up and I'll quickly walk you through the major items. Here, the Welcome section briefly describes what Cassandra is about. I won't go into video and slides for the moment. On the right-hand side, the green box shows the latest stable release that can be downloaded there. For example, version 1.2.3 at the time of this recording. We'll now move on to the overview. Here you'll find highlights of some of the most important features, along with a simple explanation on each of them. At the bottom is the Learn More tab. Further references can be found on the web. You may also subscribe to mailing lists or chat with the developers and community members. There are 5 sections: Cassandra Server, third-party distributions, Cassandra Query Language Drivers, previous and archived Cassandra Server releases, and source, respectively. Binary tarballs and Debian packages are officially provided and can be obtained here. Some third parties also provide distributions, for example, DataStax. DataStax is a third-party company developing solutions based on commercially supported enterprise-ready Apache Cassandra. The chair of the Apache Cassandra project is Jonathan Ellis, the co-founder and chief technical officer at DataStax. Cassandra Query Language Drivers, to support a SQL-like language for manipulating Cassandra, can be downloaded here, and then the previous releases if you need so. If you want to get its source code, it's available here. As Cassandra is written in Java, you may easily integrate Cassandra with popular development tools such as Maven, Jenkins, Git, and so on. A simple, concise, step-by-step installation guide is also provided. Here you may look for details of what and how you would do to contribute to the community. It's the wiki page, and many other useful hyperlinks can be found here. For example, detailed documentation is provided by DataStax. Here are some useful hyperlinks and good books for your reference. We've looked at a high-level description of what Cassandra is and ended with visiting its project website. Now you have a basic idea and know where to look for further information. Next, we're going to see Cassandra's major features and benefits. In this video, I'm going to give you a quick tour of the major features and benefits making Cassandra a leg up from the others, and several use cases showing how Cassandra is being used in production by some companies. You may not determine whether Cassandra is a good fit to your solution without knowing its features and benefits. Cassandra also helps meet the challenges of big data that the relational databases don't handle well. The real-life implementation references are also very valuable for you to know how Cassandra is used by others. Cassandra is written in Java and requires Java 1.6 or above. It supports Java Virtual Machines (JVMs) from Sun Oracle, IBM, and should also run on JRocket. The distributed model of Cassandra is based on Dynamo from Amazon and its data model on Bigtable from Google. Like Bigtable, it supports column families, providing a richer data model than the trivial key value stores. We'll go deep into column families in Section 2. Like Dynamo, it is a peer-to-peer architecture focusing on high availability at massive scale web and cloud environments. It supports multi-data center replication. Every node in a Cassandra cluster is identical, that is, no master and no slave, so it provides location transparency. Hardware failures are typical in a large clustered environment, and Cassandra is natively designed to handle those failures transparently and automatically. Data is replicated to multiple nodes, even across multiple data centers, that is, no single point of failure. Adding or removing a node in a cluster is hot, that is, without downtime. Adding a node does have performance impact while data is redistributed across nodes including the new one. So, cluster keeps working, but in a degraded mode. Nothing is free. Because of its peer-to-peer architecture, capacity can be linearly scaled. Cassandra uses the snappy compression algorithm from Google to deliver exceptional disk storage savings and significant reduction in physical I/O. It uses commit log and sequential I/O to achieve very high performance in durable write operations. It has built-in cache, and therefore eliminating the need for extra software caching layer. It supports tunable consistency, and you have choices from very strict consistency to different levels of eventual consistency. Eventual consistency is a design choice governed by the CAP theorem in distributed environment. The theorem states the trade-off between consistency, availability, and partition tolerance. Its details will be covered in Section 2. Cassandra also provides a developer-friendly query language called Cassandra Query Language, CQL. It's similar to SQL, accepting insert, update, delete, and select syntax. It provides a bridge for the developers coming from the relational world. Under the Apache Software Foundation, Cassandra is of course open source and is now very active and has large community support. If you want to look for commercial support, it's also available from third parties such as DataStax. Let's have a brief introduction of big data and its relationship with Cassandra. Big data is a term for a collection of datasets so large and complex that it becomes difficult to process using on-hand database management tools or traditional data processing applications. It's characterized by 3 V's: volume, variety, and velocity. Traditional relational databases have inherent performance and scalability limitations in dealing with big data, needless to say the possible high license costs. Cassandra particularly helps to tackle the challenges of storage, search, sharing, and transfer of big data. Okay, we've seen so many features and benefits. Let's look at some of its real-life use cases. Cassandra is perfect for big data applications, especially in dealing with real-time operational data. For example, ShopSavvy, a mobile app for shopping and price comparisons, uses Cassandra to maintain histories of price, products, scans, and locations in the hundreds of billions of items. Capacity on that scale is certainly overwhelming for relational databases. Tracking time series data is the most common use case for Cassandra. Time series data is the type of data that follows a time series pattern, such as performance metrics, sensor data, stock quotes, user activities, and so on. For example, CloudKick, acquired by Rackspace already, provides cloud server monitoring and management tools. It stores monitoring data of different metrics and rolling them up by time slices. Storing non-transactional log information from web applications is also a common use case to use Cassandra in production instead of cost-effective relational database. For example, Mahalo uses Cassandra to record user activity logs and topics for questions and answers. You may visit Planet Cassandra for more references. We've looked at the features and benefits that Cassandra can provide and some of its common use cases. Now you'd know when to use it. Next, we're going to see what Cassandra is not really good at and when not to use it. In this video, I'm going to point out the limitations and the anti-use cases that Cassandra may not be good at. Although Cassandra has so many features and benefits, as explained in the last video, it certainly has some limitations. And Cassandra is suboptimal in some applications, and I'll cover them to wrap up this video. First, Cassandra doesn't support fully ACID-compliant transactions. ACID stands for the 4 properties of a relational database, namely atomicity, consistency, isolation, and durability. As it is designed for availability at web scale, a certain degree of consistency must be sacrificed according to the CAP theorem. But it does provide the so-called eventual consistency that can be tuned to meet your needs. Second, even though Cassandra provides a SQL-like query language, CQL, it doesn't provide much support on joins and most SQL search methods, such as range query. Although range query is possible, it requires the correct design of column keys of the table. As the data modeling approach is descriptive, the design of the data model is query-driven. Non-normalized form can be used to remove the need of joins in the expense of duplicating data. It implies that the support for ad hoc query is very limited. The only way to tackle this problem is to write program code, which may be complicated. It's worth mentioning that some third-party application programming interface, API, and libraries may help to support ad hoc and joins, for example Playorm. Next, authentication and authorization are file-based, which doesn't provide either dynamic user management APIs or CQL support. Enterprise security features, such as transparent data encryption, integration with Kerberos and LDAP, are missing in community editions. It should be noted that some third parties do have commercial edition, providing such enterprise security features. It isn't difficult to understand that because of the architectural decisions, several types of applications are not suitable to use Cassandra. The most obvious one is about handling business-critical data, such as banking and insurance applications. Second, applications involving long, complex transaction logic requiring checkpoints and rollback. The workaround is to use compensating transactions that will definitely complicate the program logic. Finally, if flexible and fine-grained security features are required, it isn't Cassandra's cup of tea, or you may need to look for commercial editions. We've looked at the limitations of Cassandra and ended with some anti-use cases. Now you know what Cassandra is good at and what it's not. Next, we're going to look at some other popular NoSQL databases and compare them with Cassandra. In this video, I'm going to talk about some other popular NoSQL databases. Indeed, NoSQL is a very large family that can be divided into several categories from the architectural perspective. The number of its members is still growing, and I can only cover a few of them here. Cassandra isn't the only choice of NoSQL. There are many others. They are designed to solve different problems, but how could we differentiate them? The answer is quite simple if we'd master several differentiating factors that I'm going to show you. First, consider their data models. Most of them fall into one of the four data models, namely key-value store, column store, document-oriented, and graph-based, respectively. Key-value store is similar to the concept of Windows registry, or in Java or C#, a map, a hash, a key-value pair. Simply put, the basic unit is composed of a key and a value. Column family is basically a multi-dimensional map. The basic unit is a column that contains key, value, and timestamp. Cassandra is in this school. Then, document-oriented. It's designed for document or semi-structured data. The basic unit is a document and therefore not adhering to a standard schema. Lastly, graph-based. It's composed of nodes and relationships to form a highly connected network. The nodes and relationships can have individual properties. The second differentiating factor is distribution model. It's about how to distribute data in a cluster when scaling out. In broad terms, there are two paths to data distribution, sharding and replication. And replication can be further divided into master-slave and peer-to-peer. The first one, sharding. A shard is a horizontal partition of a database. Sharding puts the shards on different servers, each of which does its own IOs. Then, master-slave replication. It replicates or synchronizes data across multiple servers, where one of them is designated as the master or the primary, and the other servers become slaves or secondaries. It's best for read-intensive applications by horizontal scaling. Obviously, resiliency is on slaves, but not on the master. In contrast, peer-to-peer replication has all servers of a cluster applying reads and writes to all the data. No master and no slave in peer-to-peer. They are identical, and so the failure of one server doesn't compromise the whole cluster. The complication of this kind of architecture is consistency. Cassandra is this breed of animal and has its own mechanism to cope with this complication. The third differentiating factor is protocol. Many of the NoSQL databases have their own proprietary or custom communication protocols, such that the availability of the APIs for a particular programming language may be a constraint to your design. Some others do offer a more generic protocol, for example HTTP or representational state transfer, REST, making them more open for integration. You can think of many other factors, but the three above mentioned should be most fundamental. MongoDB is a document database written in C++. It is based on master-slave distribution model and provides built-in sharding and B-tree indexing support. The protocol used is called bshan. It's suitable for almost everything you would do with relational databases, but requiring a flexible data model and dynamic queries. Neo4j is a graph database written in Java with a single master distribution model. It supports node retrieval and path traversal and is ACID transactional safe. Its protocol is based on HTTP over REST. It's very good at modeling social network, transportation links, and network topology kind of data. Redis is basically an enhanced key value store developed by C++. It is also a single master model with master-slave replication. It can store data in memory with persistence option and uses Telnet similar protocol. It provides richer functions than Memcache does, and so it's very suitable for caching and real-time data collection and analytics. Then HBase. It's a distributed sorted map store, providing Google's big table-like capabilities on top of Hadoop, which is a framework allowing for the big data processing. It's written in Java and supports master-slave replication. We usually use Thrift or HTTP over REST protocol to communicate with it. It's originally designed to work with Hadoop to allow random real-time read-write access to big data. Here I made a comparison table among Cassandra and other popular NoSQL databases introduced in this video, for you to quickly grasp the essences. We've looked at some other NoSQL databases and their differences. Now you know more about the NoSQL family. Next, we're going to compare relational databases with NoSQL databases to complete this section. In this video, I'm going to compare the differences between the traditional relational database and the NoSQL database, especially Cassandra. Then you'll realize that the NoSQL database is not going to eliminate the relational database. Each of them has its own appropriate use cases. Their major differences will be explained one by one as we walk through a comparison table. Knowing their differences will prepare you well to make good, right choice on your architecture. Here I've prepared a comparison table for your easier reference. Let's go into each table item in order. The first one is data modeling. For relational databases, we need to design the data model up front by modeling the entities and their relationships in the problem domain. We want to build the best data model to reduce the chance of modifying it in the future. I call this a prescriptive process. On the flip side, by virtue of the flexible data model feature, NoSQL databases support a descriptive process, which means you can evolve the data model easily according to the queries to be supported. Care is still needed when defining keys or column names, as this will impact the usage patterns observed in the NoSQL database cluster. Then the ACID transaction properties. Relational databases, of course, provide full support. But for NoSQL databases, a certain degree of sacrifice on consistency is made to achieve higher availability and scalability to handle huge volume of data in distributed environment. For example, Cassandra doesn't support rollback transaction. Next, extract, transform, load, ETL. Because of the static relational data model, ETL, although expensive, is a typical method to build an analytical database from an operational database. Since the design of the NoSQL data model is query-driven, it's already there. ETL is generally not required. For relational databases, it's usually a single master architecture, which can be scaled vertically. On the contrary, NoSQL databases are born and designed for web scale. Relational databases can provide local clustering support for high availability. This kind of mechanism imposes limitation on the size of the cluster and inability to support geographically dispersed environment. Again, NoSQL databases are designed for availability and use in distributed environment. Implementing searching in relational databases is easily done through secondary indexes, even though some NoSQL databases, like Cassandra, support secondary indexes. There are chances of building custom search methods using complicated sort orders and slice whenever secondary indexes don't work. As relational databases have been very mature, their security is fine-grained, established, and proven. Contrarily, it can be difficult to enforce security at a granular level on NoSQL databases. Take it for granted, SQL is genuinely designed for manipulating relational databases. As NoSQL databases don't follow the relational data model intentionally, their support of SQL is usually limited. For example, Cassandra doesn't support join operations, as I mentioned previously. Relational databases are forced to make use of sharding when scaling, but NoSQL databases natively support sharding. Also, relational databases are designed to work in local data center. When they need to work across multiple data centers, other replication software or technologies are usually required. Conversely, most NoSQL databases automatically support clustering across different locations. Lastly, NoSQL databases typically support asynchronous query by design. In summary, relational databases are strong in transaction guarantee and fine-grained security, while NoSQL databases allow flexible, dynamic, evolving data model and support huge volume of data in web-scale deployment. NoSQL databases also better support geographically distributed environment. In fact, the two schools of databases are supplementing each other. Choosing either of them really depends on the problem you're solving. We've looked at a comparison of relational databases and NoSQL databases. Now you know the pros and cons of each of them. In this section, we've looked at the basics of Cassandra, its features and benefits, strengths and weaknesses, and some use cases. In addition, we've glanced at some other popular NoSQL databases and went through the differences from relational databases. Next, we're going to look into Cassandra's technical details and its inner working mechanism. It'll be the final theoretical section of this course. In this video, I'm going to introduce the CAP theorem, which is very famous in the world of NoSQL databases. Also, a closely related concept called eventual consistency will be covered. Different NoSQL databases may have different design trade-offs according to this theorem. Knowing it will help you choose the appropriate type of NoSQL database to meet your needs. Okay, let's see what the CAP theorem is. CAP is an acronym of the three characteristics of a distributed system: consistency, availability, and partition tolerance. Consistency means that all nodes in a cluster see exactly the same data at any point in time. Availability means that every request received by a non-failing node in the cluster must result in a response. Partition tolerance means that a node can still function when communication with other groups of nodes is lost. The theorem states that in a distributed system, only 2 out of the 3 characteristics can be attained at most. In other words, you can't get all 3 at the same time, and you have to make a trade-off. The relational databases such as Oracle focus on consistency and availability. Some NoSQL databases value availability and partition tolerance more, while some others are in favor of consistency and partition tolerance. Cassandra guarantees availability and partition tolerance, with a trade-off by providing eventual consistency. Eventual consistency is a compromise between strong consistency and weak consistency. Temporary inconsistency may occur in the database at a point in time, but eventually all nodes will receive the latest consistent updates. For example, in the diagram, a data is updated on the replica in node B. It will eventually be consistent across the replicas in nodes A and C respectively. Given a sufficiently long period of time without further changes, all updates can be expected to propagate throughout the system, and the replicas on nodes A and C will be consistent eventually. In practice, an update takes only a fraction of a second to become eventually consistent, so you may think that it's a trade-off between consistency and latency. Cassandra furthers it by offering tunable consistency: stronger consistency, higher latency; weaker consistency, lower latency. Cassandra can also be tuned to ensure complete consistency at the expense of availability and high availability at the expense of consistency. Contrasting with the ACID transaction properties in the relational database, the acronym BASE is used to describe such behavior. Its long form is Basically Available Soft State Eventually Consistent. Partition tolerance is a common characteristic that all NoSQL databases exhibit to support better scalability. The remaining choice is either consistency or availability, so there are 2 schools. First, partition tolerance and availability. Examples include Cassandra, CouchDB, Apache Dynamo, and so on. On the other hand, partition tolerance and consistency. Examples are Google's Bigtable, HBase, MongoDB, Redis, and so on. In the following videos, a few more topics will be covered. I will introduce Cassandra's data model in video 2. It covers data at rest. Then, write and read paths will be explained in video 3, covering data in motion. Videos 4 and 5 are about high availability, scalability, and the internal working mechanism of Cassandra. Now you better understand the constraints imposed by the CAP theorem, and should be able to make suitable selection of the type of database for your solution. Next, we're going to learn about Cassandra's data model. In this video, I'm going to talk about Cassandra's data model and its components, including column, row, column family, key space, supercolumn family, and counter column. If you're familiar with the relational data model, it may be difficult for you to understand Cassandra's data model intuitively at first glance, so I'll go through its bits and pieces from the bottom up. Column is the smallest data model element and storage unit in Cassandra. Though it also exists in a relational database, it's a different thing in Cassandra. A column is a name-value pair plus a timestamp and an optional time to live. The name and the value are byte arrays, and Cassandra provides a bunch of built-in data types which influence the sort order of the values. The timestamp is here for conflict resolution and is supplied by the client during a write operation. Time to live, TTL, is an optional expiration date used to mark the column deleted after expiration. The column will then be physically removed during compaction, which will be introduced in the next video. One level up is a row. It's a set of orderable columns with a unique row key called a primary key. The row key can be any of the same built-in data types as those for columns. What orderable means is columns are stored in sorted order by their column names. And sort order is extremely important because Cassandra can't sort by value as what we do in a relational database. Different names in columns are possible in different rows. That's why Cassandra is both row-oriented and column-oriented. It should be remarked that there is no timestamp for rows. The next level up is column family, which is basically a set of rows with a name. The row key in a column family must be unique and is used to order rows. Column family is analogous to a table in relational databases, but it provides greater flexibility by allowing different columns in different rows. This makes Cassandra being schemaless. The outermost data model element is keyspace. Keyspace is a set of column families and supercolumn families that will be introduced next. It is analogous to a schema or a database in the relational world. Each Cassandra has a system keyspace to keep system-wide metadata. Keyspace also contains replication settings, controlling how data is distributed and replicated in a cluster. Next, we talk about supercolumn and supercolumn family. Supercolumn is just a named map of columns, whereas supercolumn family is a collection of supercolumns. However, they are not recommended, since they are not supported by the Cassandra Query Language (CQL) and must be accessed by using Thrift API. Column family is enough in most cases, and so supercolumn and supercolumn family are only for your reference. Finally, counter column. It's a special kind of column used to store a number that keeps counting values. It must be in a dedicated table. Counting can be either increment or decrement, and timestamp is not required. It's interesting to note that a write to a counter column requires a read in the background. We've looked at Cassandra's data model and are now familiar with column, row, column family, keyspace, counter column, and know that supercolumn and supercolumn family are not recommended in practical use. In the next video, we're going to know more about how Cassandra writes and reads data. In this video, I'm going to describe the inner working mechanisms for writing and reading data in Cassandra. I'll also explain read repair, tombstone, and compaction. Knowing how Cassandra writes and reads data will help you understand why Cassandra can achieve such high performance. You'll appreciate the beauty of its log-structured storage design. First, let's look at a write operation. The components and their sequence of executions form a write path. When a write occurs, the data will be immediately appended to the commit log on disk to ensure write durability. Then Cassandra stores the data in memtable, an in-memory store of hot and fresh data. When memtable is full, the memtable data will be flushed to disk file called sstable using sequential I/O. And so, random I/O is avoided, and it's the reason why the write performance is so high. The commit log is purged after the flush. Due to the intentional adoption of sequential I/O, a row is typically stored across many sstable files. Apart from its data, sstable also has a primary index and a Bloom filter. Primary index is just a list of row keys and the start position of rows in the data file. Bloom filter is a sample subset of the primary index with very fast non-deterministic algorithms to check if an element is a member of a set. It's used to boost performance. For write operations, Cassandra supports tunable consistency by various write consistency levels. Write consistency level is the number of replicas that acknowledge a successful write. Write consistency level is tunable on a spectrum of consistency levels as shown on the screen. The two extremes are the leftmost, any, which means weak consistency, and the rightmost, all, strong consistency. A consistency level of 3 is very common in practice, or you may choose quorum as calculated by the given formula to be an optimum value. Here, the replication factor is the number of replicas of data on multiple nodes. Both local quorum and each quorum support multi-data center and rack-aware write consistency with slight difference as shown. Now we come to read path. When a read request comes into a node, the data to be returned is merged from all related SS tables and any unflushed mem tables. Timestamps are used to determine which one is up to date. The merged value is also stored in a write-through row cache to improve future read performance. Read consistency level is the number of replicas contacted for a successful consistent read. Almost identical to write consistency levels, except any isn't an option here. During a read, the coordinator, which is just the node that happens to be connecting and servicing the client, contacts a number of nodes, as specified by the consistency level, for data, and the fastest replicas will return the data for consistency check by in-memory comparison. As it isn't a dedicated node, it makes Cassandra lack a single point of failure. It also checks all the remaining replicas in the background. If a replica is found inconsistent, the coordinator will issue an update to bring back the consistency. This mechanism is called read repair. When a delete occurs, the data isn't physically deleted immediately. Instead, a marker called a tombstone is made to indicate the deleted data. The actual physical delete is done by compaction. Compaction is simply merge and sort SS tables to create a new SS table. It frees up space and improves performance by reducing the number of required seeks on disk. During compaction, keys are merged, columns are combined, tombstones and TTL expired columns are discarded, and a new index is created. We've looked at how Cassandra wisely handles write and read operations. You've also learned read repair, tombstone, and compaction. Next, we're going to see another very important aspect of Cassandra, its cluster architecture. In this video, I'm going to introduce the elements of a cluster and explain how Cassandra implements replication to support partition tolerance across a cluster. The network topology affects the replication strategy and hence how workloads are balanced across the cluster. By the end of this video, you will understand the replication strategies and know when and where to apply them. The cluster is the outermost structure composed of nodes in Cassandra. It's also a container of key space, typically one key space per cluster, but it may contain more than one key space. The smallest cluster, in theory, contains a single node, and a cluster of 3 or more nodes is much more practical. Each node in a cluster is identical, and so it's a peer-to-peer architecture. It holds a replica for different range of data in partitions, and exchanges information across the cluster every second. A client issues read or write requests to any node. The node that receives the request becomes a coordinator, acting as a proxy of the client to do the things as explained in the previous write and read paths video. Data is distributed across the cluster, and the node addressing mechanism is called consistent hashing. A cluster can be viewed as a ring of hash, because each node in the cluster or the ring is assigned a single unique token, such that each node is responsible for the data in the range from its assigned token to that of the previous node. For example, in the diagram, a cluster contains 4 nodes with unique tokens. Before version 1.2, tokens are calculated and assigned manually, and from version 1.2, tokens can be generated automatically. Each row has a row key, used for partitioner to calculate its hash value, that determines which node the row goes to first. The partitioner is just a hash function for calculating a row key's hash value, and it also affects how the data is distributed or balanced in the cluster. When a write occurs, the first replica of the row is always placed in the node with the key range of the token. For example, the hash value of a row key oracle is 6DE7. That falls in the range of 4,000 and 8,000, so the row goes to the bottom node first. All the remaining replicas are distributed based on the replication strategy. Replication strategy is the method of determining which nodes the replicas are placed. The default is simple strategy, suitable for single data center use without topology consideration on rack and data center location. Network topology strategy is the recommended choice. It's designed for multiple data centers and is aware of rack and data center location. In addition, the number of nodes receiving copies of the same data is configured by replication factor. That is, as already mentioned, its relationship with consistency level in quorum calculation. Typically, it's set to 3. Finally, snitch. A snitch determines which data centers and racks to go for, making Cassandra aware of the network topology for routing requests efficiently. It also affects how replicas can be distributed, in consideration of the physical setting of data centers and racks. Simple snitch is for a cluster in a single data center. Rack inferring snitch is for multiple data centers. Node location is determined by rack and data center, with reference to the node's IP address as shown in the example here. An example cluster across 2 data centers is shown. to better illustrate the relationship among replication factor, replication strategy, and snitch. Each data center has 2 racks, and each rack contains 2 nodes respectively. Replication factor per data center is set to 3. With 2 data centers, there are 6 replicas in total. Also, pay attention to the convention of IP address assignment. We've looked at the means to achieving partition tolerance and the choices of replication strategy and snitch. Now you should be able to select the most suitable replication strategy to meet your needs. Next, we're going to see Cassandra's high availability mechanism. In this video, I'm going to help you learn about Cassandra's high availability mechanism. You'll know how Cassandra takes care of availability in a cluster and grasp its failover and recovery mechanism. Some nodes in the cluster are designated as seed nodes for the others. They are the first nodes to start in the cluster, configured in cassandra.yaml configuration file. They facilitate the bootstrapping process for new nodes joining the cluster, such that when a new node comes online, it will talk to the seed node to obtain information about the other nodes in the cluster. This talking mechanism is called gossip. And so, we need to start the seed nodes one by one and then the remaining non-seed nodes. The best practice is to have more than one seed node per data center. Nodes, periodically every second, exchange state information, for example, dead or alive, about themselves and about other nodes they know about. The protocol that the nodes use is called Gossip Communication Protocol, also known as Epidemic Protocol. It's a quick, decentralized, automatic way for the cluster to learn about itself. Gossip information is persisted locally by each node to allow faster restart. One caveat: it's very critical that the list of seed nodes must be the same on each node in the cluster. A node locally determining from gossip state and history and adjusting routes accordingly using the phi accrual failure detection algorithm. Instead of the binary extremes of dead or alive, the algorithm gives a continuous suspicion level between dead and alive of how confident a node has failed. In a distributed environment, false negatives may happen due to network performance, fluctuating workload, and other conditions. The algorithm takes all these factors into account and provides a probabilistic value. If a node has failed, other nodes periodically try to gossip with it to see if it comes back online. There are 3 built-in repair mechanisms provided by Cassandra: read repair, hinted handoff, and anti-entropy. Read repair has been described, and we'll look at the remaining 2 here. Hinted handoff aims at reducing the time to restore a failed node when rejoining the cluster. It ensures absolute write availability by sacrificing a bit of read consistency. If a replica is down at the time when a write occurs, another healthy replica stores a hint. Moreover, if all relevant replicas are down, the coordinator stores the hint locally. The hint basically contains the location of the failed replica, the affected row key, and the actual data being written. When a node responsible for that token range is up again, the hint will be handed off to resume the write. As such, the update can't be read before a complete handoff, leading to inconsistent reads. Another repair mechanism is called anti-entropy, which is a replica synchronization mechanism to ensure up-to-date data on all nodes and run by administrators manually. We've looked at the high availability mechanism and how failover and recovery are designed in Cassandra. In this section, we've looked at the CAP theorem, eventual consistency, Cassandra's data model, write and read paths, and its superior clustering mechanism. Now we have a deeper understanding of Cassandra's architecture. Next, we're going to roll up our sleeves and install a single-node Cassandra that will then grow into a 3-node cluster. In this video, I'm going to introduce the recommended hardware and software requirements and system settings for Cassandra. Cassandra requires very typical hardware and software for its installation. For production use, a number of system parameters shall be adjusted with reference to the recommended settings, and I'll also describe my demonstration environment to be used over the course. The hardware requirements include those for memory, CPU, disks, and network. Cassandra supports both dedicated physical server and virtual environments such as cloud. Here, I show you the requirements for dedicated machine for production use. Firstly, CPU. A good start is 8 core. Of course, more is better. Then memory, at least 8 GB. Once again, the more the better. Disk should have at least 2 serial ATA drives, one for commit log and the other for data. Solid-state drive SSD can surely boost up performance. Similarly, at least 2 1 GB network interface cards are recommended for Thrift and RPC respectively. Be sure to read the latest Cassandra documentation before making the final hardware purchases. Second, software requirements. The officially supported platforms are Linux, including Ubuntu, Debian, Red Hat Enterprise Linux, CentOS, Oracle Linux, Mac OS X, and finally Microsoft Windows. A 64-bit operating system is recommended. Since Cassandra is written in Java, a Java runtime is required. During several installation steps, root or administrator access rights are required. In addition, software package management software is recommended to simplify the installation. Be sure to use the recommended settings as shown in the Cassandra documentation for production systems. Some are operating system related, while others are about Java. For example, Java Native Access, JNA, provides Java programs easy access to native shared libraries without using the Java native interface. For the details of these recommendations, please refer to Apache Cassandra documentation by DataStax. For this video course, I'll install, configure, and demonstrate Cassandra version 1.2.3 using VMware Workstation on a Windows 7 professional 64-bit environment in my notebook computer with Intel Core i7 2.7 GHz and 8 GB memory. You may also use other virtualization software such as Oracle VirtualBox. Since I'm familiar with VMware Workstation, I'll use its version 9.0.2 to create virtual machines as the course proceeds. Each VM is allocated with dual-core processor, 2 GB memory, 20 GB disk space, and one network interface card. This configuration is fine for demonstration purposes. The guest OS is Ubuntu 10.04 LTS Desktop Edition 64-bit version. The Linux kernel is 2.6.32, and the file system is ext4. Lastly, the Java Standard Edition runtime environment is 1.6 Update 43. Here shows the environment diagram of the following sections. In section 3.3, a single-node Cassandra will be installed by building from source code. Then, the packaged installation method will be demonstrated for another single-node instance. That single-node instance will be used as a basic building block for a 3-node cluster presented in the final section. You'll see that it's very easy to scale out the cluster with the assistance of VM cloning. Now you're familiar with the requirements and the recommended settings. You'll also know what the demo environment will be. Next, we're going to install the prerequisite software such as Java and some very handy utilities. In this video, I'm going to introduce the types of installation methods and will demonstrate how to install Java Runtime Environment, Java Native Access, and configure the system with recommended settings. I'll show you step by step on the demo environment. If you follow this video to build your own, please make sure you have internet access. Okay. Let's talk about the installation methods. 3 methods are available: binary tarball, source tarball, and distribution package. Binary tarball is a tarzip or zip file containing the ready-to-use binary files, jar libraries, and sample configuration. Source tarball is another tarzip or zip file containing the source code of Cassandra and allows you to compile and build from source. It requires compiler, libraries, and build tools to produce the binaries. Distribution package is OS-specific and similar to binary tarball. It gracefully handles complex dependencies with other packages, therefore providing a very convenient shortcut. It's the recommended method that I'll show you shortly. Now let's install the prerequisites: Java Runtime Environment and Java Native Access. Open a terminal. Add an aptitude repository by typing the command as shown on the screen. Then type sudo apt-get update and wait for the update to finish. We can now install Java by sudo apt-get install Oracle Java 6 installer. Press Enter key to continue download. Click OK to agree to the license. Click Yes to accept the license terms. When completed, type Java version. Type sudo apt-get install Oracle Java 6 set default. Then reboot the system by sudo reboot. Launch Firefox. Go to github.com/twall/jna. Scroll to the download section and click jna.jar to download. When finished, open a terminal, go to the downloads directory. Okay, you see the jar file is there. Copy and rename the jar file by typing the command on the screen. Create the symbolic link. Then we can check JNA's location. Okay, the link is already there. Now we're going to set up the system with the recommended settings. Set user resource limits. Type the command on the screen. Add the settings as shown on the screen. Click Save and close gedit. Set virtual memory. Type sudo sysctl-w vm.max map count equals 131072. Disable all swap. Type sudo swap off-all. Set read ahead. Find out the device name by typing df-h. Check existing read ahead. Set read ahead. Check again. All right. Finally, install a few more utilities. Press Enter to download. Finished. Now you know the different methods of installation and how to install the prerequisite software and configure the system with recommended settings. Next, we're going to install Cassandra by building from source tarball. In this video, I'm going to demonstrate the installation of a single-node Cassandra instance by building from its source tarball. The source tarball isn't large in size, around 11 megabytes, and includes all the stuff you need to get Cassandra up and running. I'll use the stable release version 1.2.3 as of this recording. If you want to taste the development version, please follow the instructions on the official website. The source tarball includes an Ant build script, and so we need Apache Ant to manage the compilation and build process. As Cassandra is written in Java, we need Java compiler. First, go get the source tarball. Open Firefox, go to cassandra.apache.org/download. Click the version we want, choose a mirror site, and click Save. When finished, open a terminal. Extract the files, then change to the source directory. Cassandra requires two directories for its runtime. Create them and change ownership by typing the following commands. Create the path /var/log/Cassandra. Change its owner to the current user. Then create the path /var/lib/Cassandra, and also change the owner to the current user. Then install Apache Ant, sudo apt-get install ant. When finished, type ant to build from source. When finished, set Java class path, which is very important. Make sure you set to the right directory as shown on the screen. Fire up Cassandra by typing bin/Cassandra-f. The switch F is to let Cassandra run in foreground mode, and we can then see the live log content. For convenience, the class path may be set in the .profile file in home directory so that it'll be available across logins. Another option would be to create a shell script file that sets the class path and runs Cassandra with the -f option. We now verify the installation. Open a terminal. Change to Cassandra directory. Run CQL shell by typing bin/CQLSH. Create a test schema called schema1. Then a test table called users. Insert a test record. Then try to read the record. Bingo. Now you know where to get the source tarball and how to build it from scratch. You've also seen how to manipulate the data model by using the convenient CQLSH. Next, we'll take another approach to install Cassandra by distribution package. In this video, I'm going to show you the steps to install Cassandra through distribution package. You may compare this approach with that of the last section. We'll look at the distribution packages available for different supported platforms. Then I'll show you how to install the package on Ubuntu. Apache does provide an official package for Debian Linux, but DataStax provides more choices for many popular operating systems, which are shown on the screen. DataStax provides two editions, a free-of-charge Community Edition and a paid Enterprise Edition respectively. Ubuntu package by DataStax will be used for this video. Open a terminal. First, add the software package repository. Add a source list file by typing the command on the screen. Add the repository address and save. Get the repository key. Then update the repository. When finished, get and install the distribution package, sudo apt-get install dsc12. Press Enter to proceed. After a while, the Cassandra should be set up and running. Check its status by sudo service Cassandra status. You see the Cassandra is running message. Type the command nodetool status. Nodetool is a very powerful command line administration tool for Cassandra, and you get more detailed information here. UN is shown at the leftmost column, which means up and normal. We can look into the runtime directories at /var/lib/Cassandra and /var/log/Cassandra. The configuration files are located at etc. Let's check it there. View the main file, cassandra.yaml. It's a template with defaults and annotations in detail so that the instance behavior can be configured, tuned, and tweaked here. On a high level, it includes several sections, namely initialization properties, which controls how a node is configured within a cluster, including inter-node communication, data partitioning, and replica placement. Global row and key cache properties, the caching parameters for tables. Performance tuning properties, tuning performance and system resource utilization. Binary and RPC protocol timeout properties, timeout settings for the binary protocol. RPC tuning properties cover the settings for configuring and tuning RPCs for client connections. Fault detection properties are the settings to handle poorly performing or failing nodes. Automatic backup properties about backup configuration parameters. And finally, security properties for server and client security settings. For example, in default cassandra.yaml, the cluster name is test cluster. Data file directories is the location of the data files. Commit log directory is the location of the commit logs. Seeds is 127.0.0.1, which specifies the list of the seed nodes. Listen address is localhost, and so on. I won't go into each item here and will introduce the relevant properties as the course proceeds. We can use CQL shell to connect to the instance. Type in the command cqlsh. It's connected to test cluster at localhost port 9160. Then switch to the system keyspace. Use system semicolon. And select asterisk from peers semicolon. No record returned is the expected result as it's a single node instance. Well done. Now you know how to get the distribution package based on your needs and have seen my demonstration on Ubuntu. You also had a look at several important Cassandra directories and its configuration file cassandra.yaml. Next, we're going to scale out this single node instance to a 3-node cluster. In this video, I'm going to grow the single node instance set up in the last video into a 3-node cluster. To quickly set up a cluster for this course, we'll properly configure the single node VM as a seeding VM, node 0, and use the cloning feature provided by the VMware Workstation software to create the remaining two, node 1 and node 2 respectively. Particularly important is the settings of the cluster network. A convenient tool called cluster SSH is also installed to ease your management of the cluster. The higher level steps are shown on the screen. Because the demonstration environment is based on Ubuntu and VMware Workstation, the steps are supplementary information and are not covered in this video. Please refer to Section 8 of this course for further details. Let's assume that the nodes and their network are properly created and set up. It's time to configure the Cassandra cluster. Launch cluster SSH by CSSH node 0, node 1, node 2. Apart from the cluster SSH command window, 3 SSH windows come out as well. In the command window, type in cd/etc/Cassandra and press Enter. List out files in the directory. Make a backup of cassandra.yaml before changing it by cp command. Check if the backup file exists. Alright, it's there. Then edit the configuration file. Several parameters need to be changed. First, change cluster name to packed cluster. Then change num tokens to 256. Then seeds, change it to node 0. Next, set RPC address to 0.0.0.0.0. Also, change endpoint snitch to rack inferring snitch. Finally, use each individual SSH window to change listen address to its corresponding hostname. For example, in node 0 SSH, change listen address to node 0, and so on. Go back to the cluster SSH command window. Type escape:/WQ to save the files. Next, we'll start up the cluster. In node 0 SSH, start the Cassandra service. Check the service status. It's running. Check the node status by node tool. The node is up and normal and serves 100% loading. Then go to node 1 SSH. Start Cassandra. Check the node status. The result still shows node 0. Yes, it's node 0. Do you remember the gossip protocol? Node 1 takes about 1 minute to bootstrap. After 1 minute, node tool status again. It's up and normal and serves part of the loading, around 49%. Start up node 2 and keep waiting for about 1 minute. Node tool status shows all 3 nodes are up and normal, each sharing about 1/3 of the loading. We then test the cluster by shutting down the Cassandra service on node 2. Check the status of the service. Okay, Cassandra is not running. Go back to node 0 SSH window, check the status of the cluster again. It shows node 2 is down and normal, which means node 2 is temporarily leaving the cluster. Now you've seen how to set up a cluster. In fact, it isn't difficult when a seeding node is set up properly. In this section, we've quickly gone through the 3 types of Cassandra installation. You'd be able to build your own now. Next, we're going to set up monitoring for the cluster, and I'll demonstrate how to use the tools efficiently. In this video, I'm going to introduce the logs of a Cassandra database cluster. They're very valuable for monitoring, problem diagnosis, troubleshooting, and performance tuning. Proper log rotation is also required for a production system, and I'll introduce it in this video. By default, Cassandra generates 2 log files for its activities. First, system.log, Cassandra's server log, located at /var/log/Cassandra. Because the logging implementation is log4j, the log is configured in log4j-server.properties file. Second, output.log, the standard out of the Cassandra process. Its default location is the same as that of system.log. However, differing from system.log, it isn't controllable from log4j. Log4j is a very common logging library for Java, and similar to Cassandra, is also an Apache Software Foundation project. Log4j defines logging levels as illustrated in the table. Trace is of the highest severity, then debug. Info is the default, suitable for normal production system. Further down the table are warn, error, fatal. And at the bottom, off means turning off logging completely. If something bad happens, logging level should be increased to debug or even trace by modifying log4j.rootLogger in log4j-server.properties. In a production system, we usually keep the log files for a longer period by keeping backups through proper log rotations. Log rotation involves two things, the size and the number of the backup log files. For system.log, log rotation is configured in log4j-server.properties. Output.log rotation setting is done by logrotate utility. Now let me show you how to configure the logs and their rotation settings. Change to /var/log/Cassandra. You see system.log and output.log are there. View system.log. Many lines beginning with info are shown. To look for any warning inside, type / and big letters warn. One is found complaining about no host ID found. You may search others such as error. Let's have a look at output.log as well. Very similar to system.log, many info lines are there. Any warning? Oh, the same warning. No host ID found. Change to /etc/Cassandra. Open log4j-server.properties. Here is to configure the root logger's logging level. It's info by default. You may also change the line layout. Moreover, you may have finer-grained capture on particular Java packages or classes. System.log rotation is configured here. Output.log rotation isn't controlled by log4j. Let's change to /etc logrotate.d. Create and edit a file called Cassandra. I want the output.log files to be 20 megabytes in size and a rotation containing 50 output.log files. Type in the commands as shown on the screen, and lastly, save the file. Now you're familiar with system.log and output.log and how to configure their log rotations. You are strongly suggested visiting log4j's website to obtain more information. Next, we're going to learn about a powerful command line utility provided by Cassandra, Node Tool. In this video, I'm going to show you the frequently used command line utility, Node Tool. You may use it to do almost everything with Cassandra. Common monitoring tasks, such as node level monitoring and ring level monitoring, will be explained in depth, followed by a brief introduction of miscellaneous monitoring commands. Node Tool is bundled with Cassandra installation. The default location is under Cassandra bin directory, or the /user/bin directory on Linux, depending on the method you used to install Cassandra. It's basically a shell script wrapping a Java class, org.apache.cassandra.tools.node command. It's not only used for monitoring, but also allows managing and controlling Cassandra's behavior. The syntaxes of standard usage and RMI usage are shown on the screen respectively. Let's see how to use it. Find out the location of Node Tool by which command. You see that it's in /user/bin directory. Open the file and see its content. So, it's a shell script, and here is the Java class. To get a brief description of how to use it, simply type Node Tool without arguments, and an online help will be displayed. Here is the usage syntax, a bunch of arguments and available commands. H is the most frequently used argument to specify the host name or IP address of the node, and status is a handy command to show the cluster information. Let's go deeper into node and cluster monitoring with Node Tool. Use the info command to obtain some basic information of the connected node's current state. Host name argument indicates the node to be connected. The information includes token, loading, gossip and thrift state, uptime, heap memory, data center and rack, exceptions, key, and row caches. Here is a terminal on node 0 of the 3-node cluster. Type node tool info. It displays the information of the local node, that is, node 0. For instance here, the host ID. Gossip and thrift are both active. The node has been up for 427 seconds. The heap consumes about 125 megabytes memory. The data center and rack location of the node. Any exceptions raised previously. And some metrics on the key and row caches. To see remote node's information, use H argument to specify the target node. For example, type node tool -h node1 info to see node 1's information. Alright. Use the ring command to determine the ring of the node and get some basic information of the ring's current state. The information includes address, data center and rack, status, state, load, and token. Type node tool ring. a long list comes out showing the address, status, state, loading, and token information. For example, this line shows a node whose IP address is 192.168.0.147, is up and normal, sharing 31.59% of the overall loading and the tokens under its control. The status command also shows the information of a cluster, but in a summary format. We've used it several times to conduct verification tests in the last section. It's less verbose than the ring command. The information includes address, status, state, load, and token. We're now still on node 0. Type node tool status. A much shorter list shows the summary information of the same cluster. UN means the node is up and normal, then the IP address of the node, the load, and number of tokens. The current loading of the node in percentage, now serving 31.6%, host ID, and finally the rack. Node tool has many more commands to provide information on particular areas. Several of the commands are highlighted here, namely statistics on column family, compaction, network and thread tool, gossip information, read-write latency, and so on. A short video can't illustrate all of the functions of node tool. Some of them will be introduced while the course proceeds. You may read the reference and the official documentation. We've gone through a quick overview of the command line node tool. You should master its usage for day-to-day Cassandra administration and monitoring. Next, we'll learn about another very powerful tool in graphical user interface. It's JConsole. In this video, I'm going to show you a GUI monitoring and management tool for Cassandra called JConsole. It isn't built specifically for Cassandra. With Cassandra's Java Management Extensions, or JMX, support, it becomes a one-stop shop for maintenance and management. JConsole is a JMX-compliant GUI tool. It has the advantage of easier identification of trends and patterns. It's bundled in Java SDK since version 5, and so it's free of charge. It also permits local and remote management through Remote Method Invocation, RMI. However, it's resource-intensive and is recommended to run on a separate machine. And each manageable resource inside JVM is called a managed bean, or mbean for short. Currently, JConsole groups a myriad of information into 6 tabs. The mbeans tab is the most important area for specific metrics and operations exposed by Cassandra's mbeans, which will be covered later in this video. JMX support is controlled through a few JVM options, which are configured in the central cassandra-env.sh. The default JMX port is 7199. You may change to other value at will. You may enable Secure Socket Layer, SSL, or turn on authentication. Okay, let's watch a demonstration. Change to /etc/Cassandra. Use vi to edit cassandra-env.sh. Search for JMX. The default value of the JMX port variable is 7199 that is used for JMX access. Then search for JMX remote. Here are the default settings. As an illustration, I'll enable authentication to ban anonymous access. Change com.sun.management.jmxremote.authenticate to true, and add a new line as shown on the screen to specify the location of the username password file. Save. Create the username password file called jmxremote.password. Insert the username monitor role, press the tab key, and input the password ABC123. Save. To secure this authentication file, change the jmxremote.password file to mode 600 and its owner and group to Cassandra. Restart Cassandra. Check its status. Launch JConsole. In the login prompt, input localhost 7199, input monitor role, and ABC123. Click Connect button. We can now see the 6 tabs. The first tab is Overview, presented as a dashboard of the system status. Then the Memory tab, mainly focusing on heap memory trends and metrics. Then the Threads tab, relating to thread pool statistics and trends. The fourth tab is Classes. The second to last tab is VM Summary, showing a summary of the JVM being used. Finally, the mbeans tab. Before we look into this tab, let's learn about Cassandra's mbeans first. Cassandra provides a few mbean packages to allow you to issue operations and monitor its metrics. The DB package focuses on caching, table metrics, and compaction. Then the internal package for internal server operations such as gossip, hinted handoff. The metrics package provides internal metrics such as client read-write request latencies, column families Bloom filter false positive ratio, and so on. The net package is about internode communication. Then the request package for tasks related to read, write, and replication operations. Finally, the service package gives information about node, ring, token, snapshot, etc. These mbean packages can be found in the tree on the mbeans tab of JConsole. Here shows a summary table of the mbean packages with their metrics and operations for your quick reference. The details can be found in the reference provided. Let's return to the mbeans tab of JConsole and browse some mbeans. The mbean packages are shown in the tree on the left. Unfolding each of them shows its classes, properties, attributes, and operations. For example, expand cache of the metrics package, key cache class, capacity properties, and select attributes. As key cache has only one attribute, the capacity of the key cache configured, its value is shown on the right. One more example, expand read stage class of the request package and select attributes. This time a few more attributes are shown on the right. For example, completed tasks is 1 and pending tasks is 0. You've been familiar with JConsole and how to use it with Cassandra. Indeed, JConsole is very powerful yet very complicated. You should read the documentation and master its usage. Next, we'll delve into Java Garbage Collection and learn about how to monitor it for Cassandra. In this video, I'm going to talk about Java Garbage Collection, GC in short. Cassandra is written in Java, and so it relies heavily on JVM's performance, which is in fact impacted by GC. GC log configuration and interpretation will be presented respectively. A detailed look at how to tune up JVM and GC performance will be covered in Section 7. A garbage collector must be included in a Java virtual machine to reclaim unreachable objects and hence their memory. In Oracle's Hotspot JVM, the garbage collector is implemented based on the weak generational hypothesis, which states that most allocated objects become unreachable quickly and few references from older to younger objects exist. The heap is split into 3 generations. The first one, young generation. It contains mostly newly allocated objects and subdivided into Eden space and survivor space. GC on young generation is called minor GC. The survived objects will be promoted to the second generation, known as old generation. It holds longer-lived objects, also known as tenured generation. GC on old generation is called full GC. The third one is permanent generation, which basically holds metadata only. GC activities can be recorded in log files. Because GC logging consumes system resources, it's disabled by default in Cassandra. Enable it only when you need it in tuning or diagnosing GC performance. If required, manual GC can be executed in JConsole to generate records in GC log. GC log is configured through JVM opts variable in cassandra-env.sh. A template of GC logging options is provided inside. GC log rotation is supported by JDK 6 Update 34, JDK 7 Update 2, or later. It's also configured in cassandra-env.sh. Check if GC log exists in /var/log/Cassandra. Change to /etc/Cassandra. Edit cassandra-env.sh. Search for GC log. Uncomment the relevant lines. Save and start Cassandra. Check /var/log/Cassandra. A GC log is generated there. Then enable GC log rotation. Edit cassandra-env.sh again. Search for GC log. Uncomment the relevant lines. Save and restart Cassandra. Check /var/log/Cassandra. gc.log.0 is generated, proving GC log rotation configured successfully. In GC log, minor GC that collects young generation spaces is recorded with the syntax shown on the screen. A keyword, ps_young_gen, indicates a minor GC. Both the size change of young generation space and the GC elapsed time are very important. Minor GC shouldn't take too long and should reclaim significant space. Full GC that collects young generation spaces, collects and compacts old and permanent generation spaces, is recorded with the syntax shown on the screen. It's much longer than minor GC. A keyword full indicates a full GC. Both the size change of generation spaces and the GC elapsed time are very important. GC is a broad and important topic, and you may visit the provided web pages for further information. Now you have a quick understanding of how GC works in the hotspot JVM. Please note that different JVM products have different GC behaviors. You should always consult the corresponding documentation. Next, we're going to see which system monitoring tools can be used to monitor Cassandra and how to perform health check easily. In this video, I'm going to introduce the system utilities that can be used to monitor the day-to-day operations of Cassandra. System-level monitoring includes the most basic aspects, such as the statistics of CPU, memory, disk I/O, and network activity. I'll also provide a very brief checklist on Cassandra's health status. Finally, more advanced tools will be named for your own exploration. Since most Cassandra deployments are Linux-based, Linux system-level monitoring tools are the primary focus. However, I'll introduce their alternatives on Windows platform for reference. vmstat is found in almost every Unix or Linux system. A quick glance can give a high-level understanding of the current system status. Attention should be paid on the amount of virtual memory is used. The percentage of CPU time is another area of focus, especially the wait. Another common system tool is mpstat. It's included in the sysstat package. It provides a profile of the utilization of each CPU. You should watch out the percentage I/O wait to see if waits are very frequent. Top utility provides an ongoing look at processor activity in real time so that you can find out the busiest processes running in the system. IOstat can report important metrics of every physical I/O device, for example, the number of I/O requests per second, the number of blocks read and written per second, etc. Next, netstat is the most typical tool. Particularly for Cassandra, the TCP ports used by Thrift and JMX should be monitored. The above-mentioned tools are all Linux-based. For Windows platforms, there are two system built-in monitoring tools, Resource Monitor and Performance Monitor, providing similar functions. Resource Monitor helps to identify which program or service is using resources. Performance Monitor examines how running programs affect the computer's performance, both in real time and by collecting log data for later analysis. Both tools are available in contemporary Windows versions. You may visit the websites for further information. The following steps can provide a quick health check of a Cassandra database cluster. First, check the system-level statistics, such as CPU and memory, as mentioned above. Second, check if errors are recorded in system.log and output.log. Then, check the completed tasks and pending tasks of the mutation stage mbean. Completed tasks should be increasing, whereas pending tasks should be pretty stable. Lastly, check dropped message mbean. If the dropped attribute of various stages is increasing, it's an indication of server overload. Let's see how to run a simple health check of the Cassandra set up in Section 3. Change to /var/log/Cassandra. Use grep to find out any error in output.log, then system.log. Alright, no error is reported. Launch jconsole. Go to mbeans tab. On the left Explorer, expand org.apache.cassandra.request. Expand mutation stage and select attributes. Completed tasks shows 14 and pending tasks is 0, so it's fine. Next, expand read stage and select attributes. Again, completed tasks is 1 and pending tasks is 0. Good. Finally, check dropped message. Expand org.apache.cassandra.metrics and dropped message. Then expand mutation, dropped, and select attributes. The count is 0, showing that no request is dropped for data write. Then expand read, dropped, and select attributes. The count is 0 again. Great. There are some more powerful tools, providing more in-depth view and analysis. For example, Ops Center from DataStax, providing a graphical interface for administrators to visually manage and monitor Cassandra. You may download the Community Edition to have a try. I won't go through all of the advanced tools here, and you may visit their websites for more information. A bunch of system-provided tools can be used to monitor Cassandra's basic operations and performance. Also, jconsole is another great tool to dive into Cassandra's internal statistics and metrics. In this section, you've known how to set up, configure, and use the logs, command line tools, GUI tool, Java garbage collection statistics, and system tools to monitor Cassandra from various perspectives. Next, we're going to manage the data import and export procedures. There are indeed many methods and tools provided to do so, and I'll illustrate how to use them through demonstrations. In this video, I'm going to introduce how to load a huge amount of data into Cassandra using SS Table Loader. Indeed, it's a little bit difficult and requires several steps and more than one tool. I'll show you how to streamline the steps to load Facebook daily stock quotes collected from Yahoo Finance into Cassandra by SS Table Loader. Let's have an overview of the bulk load process and work backwards from part 2 on the diagram. Cassandra provides a tool called SS Table Loader that can stream SS Table data files into a running cluster, conforming to the replication strategy. Alternatively, one may use a provided JMX mbean to achieve the same bulk load purpose. Since SS Table is for data only, the schema of the target table must be defined in the cluster through Cassandra CLI or CQLSH. However, both SS Table Loader and JMX mbean only accept SS Table as their input. As such, we need a way to generate the SS Table. I developed a Java program, packeddataimport.java, to load the data in comma-separated values, CSV, and generate the input SS Table. It's what part 1 outputs. Packedrun.sh is simply a shell script to set Java class path and streamline the execution of packeddataimport.java. Packeddataimport.java is not provided by Cassandra. I made it for this video by modifying a third-party Java program available at GitHub called dataimport.java. The major change is to replace random partitioner with murmur3 partitioner, which is the recommended partitioner for Cassandra version 1.2 or above, and make the program to handle CSV data and generate SS Table easier. Partitioner will be introduced later in the primary indexes video. In packedrun.sh, I properly set Cassandra home and Cassandra config variables, and include the Cassandra jar libraries in the class path to run packeddataimport.java. SS Table Loader streams SS Table into a cluster according to the replication strategy. It uses Gossip Protocol and therefore requires Cassandra.yaml configuration file in the Java class path to locate the seed node. It can be run in parallel to speed up the upload. The location of SS Table must follow the format as shown on the screen. Please note that the schema of the table is not created by SS Table Loader and has to be defined by Cassandra CLI or CQLSH. Instead of SS Table Loader, Cassandra also provides a bulk load operation in its storage service mbean. You may visit the given URL for further information. I'll give an example of loading Facebook daily stock quotes in May 2013 in a Cassandra table. The quotes are in CSV format and can be downloaded at the URL provided. The fields of the CSV file include the date of the quote, the open, high, low, close prices, the volume, and the adjusted closing price. The target table is called FB under the quote keyspace. I'll use Cassandra CLI command to create the quote keyspace and the FB table. The column names should match the fields of the CSV file. Here are the high-level steps of the demonstration. Download the stock quotes, generate the SS Table, define the target table, upload the SS Table by SS Table Loader, and finally, verify the loaded data by CQLSH. As shown, packeddataimport.java and packedrun.sh are placed in Demo5 directory. Now download the Facebook stock quotes from Yahoo Finance with the wget command as shown and save it as fb.csv. Check its content by gedit. The data is here, and a top row describes the column headers. All right. Then, execute packedrun.sh quote fb fb.csv. 23 lines are parsed, including the header row, so there are only 22 rows of data. The generated SS Table file is in quote/fb directory. Run Cassandra CLI. Create keyspace quote. Use quote keyspace. Create a column family called FB. Okay, exit to the shell again. Type SS Table Loader -d localhost quote/fb and press Enter key. The SS Table file should be uploaded successfully. Let's check it by CQLSH. Use quote keyspace. Count the rows of table FB. 22 rows are there, matching the input CSV. Show the content of FB. All right. Now you understand how to generate SS Table using the provided program and load the SS Table into Cassandra through SS Table Loader. It's a bit clumsy, right? Next, we're going to look at a more convenient way of data import and export using JavaScript object notation. In this video, I'm going to show you how to import and export data using JavaScript Object Notation, or JSON. This method is much more convenient than the SSTable loader method presented in the last video. Cassandra provides command line tools for JSON data import and export respectively. I'll briefly introduce what JSON is, the usage of the import-export tools, and demonstrate how to use them in this video. First of all, what is JSON? It's an acronym of JavaScript Object Notation. It's a lightweight, text-based data interchange format, being an alternative to the much more complicated extensible markup language XML. It's human-readable and programming language independent, which is supported by virtually all modern programming languages. It's often used in Ajax to provide desktop computing user experience in a web browser environment. Basically, it has two structures, a collection of name-value pairs and an ordered list of values. One potential pitfall is that numbers can be served either as numeric literals or quoted strings. Cassandra provides a tool called SSTable to JSON that can convert on-disk SSTable of a column family into a JSON file. You may use switches to include or exclude specific keys in the export, or simply enumerate only the keys without data. The output format of the JSON file follows the pattern on the screen. You'll have a clearer picture after the demonstration that exports the rows in the FB table into a JSON file. To access the Cassandra data directory, we need the root privilege. Type su root. Change to /var/lib/cassandra/data/quote/fb. Show the files inside. Switch to another terminal. Type sudo sstable to JSON. We need to find out the name of the SS table. Copy the path of the SS table and paste it to the sstable to JSON command. Add a slash and copy the name of the data file. Paste it and redirect the output to fb2.json. Okay, fb2.json is generated. Let's check its content. Each record can be easily identified. On the flip side, JSON to SSTable is provided to convert a JSON representation of a table to an SS table. Key space and table must be specified, and they are not automatically created by this tool, meaning that the key space and the table have to exist in the cluster. JSON file is the source JSON file containing the data to be imported. SSTable is the full path of the data file to be generated with the naming convention as shown. Let's import the fb2.json into another table called fb2. Firstly, create the target table, fb2, in quote keyspace. The schema of fb2 is the same as that of fb. Exit to the shell, then sudo json to sstable -k quote -c fb2 fb2.json. Get the full path of the fb2 SS table. Give the name of the data file, quote fb2 ib1data.db. Okay, 22 keys were imported successfully. Refresh the column family by node tool refresh quote fb2, then use CQLSH to verify fb2's records. Use quote keyspace, select star from fb2. Alright. You've now known how to use SSTable to JSON and JSON to SSTable. They are very handy to export and import Cassandra data in JSON format. In addition to JSON, CQL has provided a native copy command to export and import CSV file. Next, we're going to learn how to use it. In this video, I'm going to introduce the copy command supported in CQL. It can be used to import and export CSV file much easier than the traditional SSTable loader. Since it's natively supported by Cassandra, third-party programs are not required. Short demonstrations are also provided to illustrate its usage. First, let's have an overview of a CSV file. CSV is an acronym of comma-separated values. It's a common, plain text format suitable for tabular data. Most spreadsheet software, such as Microsoft Excel, supports it. It may consist of any number of records, but requires each record to contain the same number of fields or columns in the same sequence. As its name suggests, fields are separated by a delimiter, usually a comma. Another popular delimiter is tab, and therefore a tab delimited file. If the data has fields containing the delimiter character, the addition of escape characters is required and the format can get complex. From version 1.1.3, Cassandra provides the copy command in CQL to greatly simplify the clumsy import-export steps of using SS Table Loader. The copy command can import and export CSV by just a single CQL statement, and direct manipulation of SS Table is not necessary. It can even support import from standard input and export to standard output, so it's very convenient. Copy can be used to export data with the syntax as shown. It exports the data in the given table with the columns specified in the parentheses to either a file or the standard output with a bunch of export options as displayed in the table below. The first 4 options are self-explanatory, and I won't go through each of them. Encoding is used to specify the character encoding of the output file. Typically, Unicode can fit into most cases. Null is used to set the value to represent an empty value. Okay, let's see how to export the data in the FB table to a CSV file called fb3.csv with a slightly different order of the columns. Open CQLSH. Use quote keyspace. Type the copy command statement as shown on the screen. Pay attention to the sequence of the columns in the parentheses. The date column is put last. 22 rows were exported. Let's check the contents of fb3.csv. gedit fb3.csv. So each column is delimited by comma, and the date is the last column of each row. On the flip side, the syntax of copy to import data is shown on the screen. It imports the data in the given table with the columns specified in the parentheses from either a file or the standard input, with a bunch of import options as displayed in the table below. The options are the same as those for export. Let's create a new table called FB3 and import the data in fb3.csv into it. In CQLSH, create a new table FB3 with the columns and primary key as shown. Then type in the copy command. Copy FB3 from the demo data source file fb3.csv with header equals to true, semicolon, press enter key. Okay, 22 rows were imported. Let's view FB3's contents. Select star from FB3. Okay, here they are. Now you're familiar with the copy command. You've also learned about the various tools and commands for data import and export. Next, we're going to turn to another very important topic, primary and secondary indexes. You need to understand their differences so as to use CQL correctly for queries. In this video, I'm going to help you grasp what a primary index is in Cassandra. The related concepts, for example, compound primary key, composite partition key, and partitioner, will also be introduced. The reason why Cassandra is a good fit for time series type of data is also explained. The row key is what determines what machine the data is stored on, that is, node location. And primary index is indeed a list of row keys and the start position of rows in the data file. CQL keywords primary key are used to specify the column to be indexed. Each node maintains its own primary index for the data it manages, and rows are assigned to nodes by cluster-configured partitioner and keyspace-configured replication strategy. Since each node knows what range of keys each node manages, rows can be located by scanning the row indexes only on the relevant replicas. However, Cassandra doesn't enforce uniqueness on primary key, which means inserting a duplicate row key will actually upsert, that is, update and insert, the columns. Primary key can be composed of more than one column, which is called compound primary key. It guarantees clustering or ordering per partition. Cassandra uses the first column as the partition key to determine the node to store the row, and uses the remaining columns as the clustering columns for ordering of data. Here, the partition key is C1, and the clustering columns are C2 and C3. On a physical node, when rows for a partition key are stored in order based on the clustering columns, retrieval of rows is very efficient. Actually, the partition key can also be composed of more than one column, called composite partition key. It's defined by an extra set of parentheses in the primary key clause. The partition key is now composed of C1 and C2, and the clustering columns are C3 and C4. Internally, Cassandra concatenates the columns in the partition key together as an internal row key. The clustering columns are also concatenated together as prefix used in the names of the normal columns, such as C5 and C6 in the example above.
Cassandra is very suitable for handling time series type of data, such as web server log files like Apache or Nginx, usage, sensor data, SIP packets, and so on. For a simple example, to record the data stream of server loading, we may intuitively design a column family called server loading, holding 3 columns: server ID is the row key, timestamp of measurement, and loading. Because server ID is the row key, the size of the row will quickly become gigantic over time. A better way of not overwhelming the row is to add one column, such as date, as a compound primary key with server ID. This date bucket pattern can then limit the size of the rows on a daily basis, making the rows more manageable. Now let's talk a little bit about partitioner. It's a hash function to calculate the token of a row key, and so it determines how data is distributed across the nodes in the cluster. There are 3 choices. First, Murmur3 partitioner, the default since version 1.2. It uniformly distributes data based on Murmur hash 64-bit hash values. But beware that rows are ordered by hash value, not the row key. You may use the token function to page through all rows. Next, Random partitioner, the previous default partitioner based on MD5. It's very similar to Murmur3 partitioner, except a bit slower. Finally, Byte-ordered partitioner. It keeps an ordered distribution of data lexically by key bytes, so that token is calculated by looking at actual row key value, making ordered scans and range scans by primary key possible. But it has many drawbacks, such as difficult for load balancing, write hotspots, and uneven load balancing for multiple tables. Okay, let's go to watch a short compound primary key demonstration. Add 2 more columns, the stock exchange NASDAQ and the symbol FB, to fb.csv by the awk command as shown, and redirect the output to fb4.csv. Verify fb4.csv. OK. Open CQLSH, use quote keyspace. Create a new table fb4 with symbol and close as a compound primary key. Use the copy command to import data from fb4.csv. Select the rows. OK. Let's query by some criteria using the primary key. Select all Facebook rows having day close higher than 26. Many rows are there. Then, find out the row with the lowest day close, that is, the first row when ordered by close. It's on the 29th of May. OK. Now you know what a primary index is and how it works in Cassandra. Next, we'll learn about its counterpart, secondary indexes. In this video, I'm going to talk about the secondary indexes in Cassandra. Since each table can have only one primary index, secondary indexes can be created to index columns not in the primary key. It is not equivalent to the secondary indexes in the traditional RDBMS and will be explained shortly. The commands and utilities used to maintain secondary indexes will also be introduced. Cassandra supports secondary indexes on columns other than those in the primary row key to find rows not using the row key. Each table can have more than one secondary index. Behind the scenes, it's implemented as separate hidden table maintained automatically by the internal process. It doesn't support collection column types and can't be created on the primary key itself. It's most efficient when using equality predicates. It's indeed a limitation that must have at least one equality predicate clause to hopefully limit the set of rows that need to be read into memory. It can apply additional filters to the result set for values of other columns by allow filtering clause that is usually used in a potentially expensive query, such as a range query. The major difference between primary and secondary indexes is that primary index is a distributed index, while secondary index is a local index. Primary index is used to determine the node location across the cluster, and so for a given row, its node location can be found immediately. However, secondary index is just to index the data on the local node, and it may not be possible to know immediately the locations of all matched rows without having examined all nodes in the cluster. Thus, the performance is unpredictable. So secondary indexes are best on a table having many rows that contain the indexed value. That is low cardinality in the relational database terminologies, which is counterintuitive to the relational people. The more unique values in a particular column, the more overhead to query and maintain the index. Therefore, it's not suitable for querying a huge volume of records for a small number of results. A better workaround is to manually maintain a table as a form of an index, but it requires client application to populate the table with data. To create secondary index, use createIndex statement in CQLSH. Remember, columns in secondary index must not be columns in primary key. To drop index, simply use dropIndex statement. Sometimes you need to rebuild the secondary indexes online. Use node tool rebuild index. To find out the secondary indexes of a table, use describe table in CQLSH. Let me demonstrate the use of secondary indexes. Open CQLSH. Use quote keyspace. Select all stock quotes belonging to the NASDAQ Stock Exchange. Oops, an error. It's because exchange is not in primary key, and so it can't be used in the where clause. Symbol is in the primary key. Let's try to include it in the where to see if it works. Still no luck. Append allow filtering to give it a try. No indexed columns present in by columns clause with equal operator. Of course, allow filtering is used with secondary indexes. Let's create a secondary index called FB4 Exchange on the Exchange column. Describe table FB4. Primary index is here, and secondary index is here. Try the queries again. It works. Try to select stock quotes in NASDAQ having day high more than 29. Error again. It recommends using allow filtering because of the mentioned unpredictability. Add it and try again. Okay, now, query using both primary index and secondary indexes is fine. Select all Facebook stock quotes in NASDAQ with day high more than 29 and day close higher than 28.5. Good. Even the columns not in primary index and secondary indexes can be used to filter results. Select all Facebook stock quotes in NASDAQ with day high more than 29 and day open higher than 28. Note that open is not in any index. It's done by the additional filtering process of Cassandra. All right. Now you know what a secondary index is and when and how to use it. You should also grasp the difference from the primary index and be familiar with its maintenance commands and tools. In this section, we've looked at various methods of data import and export, as well as the primary and secondary indexes. Next, we're going to learn about how to perform data backup and restoration. Cassandra supports different backup methods, and I'll explain how to use them through demonstrations.
In this video, I'll explain the concepts of backup and recovery in Cassandra. Its mechanism is actually quite different from that of the relational databases. I'll list out what needs to be backed up, including both system configuration and data. Then, the different types of data backup and restore methods will be introduced. Finally, I'll prepare a keyspace and table for the demonstrations. Backup in Cassandra should not involve data only. We must take into account its configuration files so as to restore the whole system. The configuration files include, first, Cassandra.yaml. It's the most important one, storing the node and cluster configuration. Then, password.properties and access.properties. They store the configuration for authentication and authorization, respectively. Lastly, log4j server properties. Learned in the previous section, you know it's for system log configuration. The log files, such as system log and output log, are also important assets of the system that need to be backed up. Cassandra doesn't provide tool to back up the configuration and log files, and therefore we need to back them up manually. We know that data is stored in SS tables, and Cassandra does provide native data backup tools that are introduced in the next slide. If we focus solely on the data itself, we can use CQLCopy command to export the data into CSV files. Alternatively, we can use SSTable2JSON utility to export the data in JSON format. These two options don't include metadata information, and we need to take care of it ourselves. Another choice is taking snapshot of SSTable by node tool snapshot command. It supports online full snapshot and online incremental backup as well. However, it's for a single node only, which means we require to use parallel SSH tool to snapshot an entire cluster. Although full snapshot is similar to a full backup of a relational database, it's fundamentally different in that no one node is guaranteed to be consistent with its replica node at the time a snapshot is taken because of the massively distributed architecture. On the flip side, data can be restored by importing the CSV files and JSON using copy command and JSON to SS table, respectively. Both require us to create the target keyspace and table manually before the import. Cassandra supports point-in-time recovery using SS table, but it doesn't provide a native recovery tool to do the job. Only a recovery procedure is provided in its documentation. It is executed offline, and the above-mentioned inconsistency can be resolved by Cassandra's consistency mechanism, such that data consistency will eventually be resumed. Here I'll show you the creation of a sample keyspace and a sample table in the 3-node cluster that was built in Section 3. In another terminal, open CQLSH. Create keyspace BK using simple strategy, and the replication factor is set to 2 with the command as shown. Use BK keyspace. Create table T with 2 columns, C1 and C2 respectively. Okay, now you've grasped the backup and recovery concepts of Cassandra. You also know that backup should include the configuration and log files other than the SS tables. Next, we'll drill deeper into the snapshot mechanism and learn how to take full snapshot of a cluster. In this video, I'm going to introduce snapshot in Cassandra. It's the native way provided by Cassandra for making full data backup. I'll explain its mechanism and the configuration options that are available. Then, I'll demonstrate how to use node tool command to take snapshot in a cluster. Cassandra uses a log-based mechanism to store data in SS tables that are written once only and will never be edited again. This makes point-in-time snapshot data backup quick and easy. When we take snapshot, the data in memtable will be flushed to disk, and then a folder will be created to store the hard links of the SS tables for each keyspace at the time of snapshot. On Unix or Linux, a hard link maintains the data on disk even if the associated SS table is subsequently deleted. The snapshot folder is named by the timestamp in a snapshots folder in the table directory on each node. Be sure to run snapshot on each node in the cluster. We can take multiple snapshots, but must ensure the free disk space is sufficient because the hard links created now and before consume a certain amount of disk space. Node tool snapshot command is used to take snapshot of a keyspace on a single node. To take snapshot of an entire cluster, it's more convenient to use third-party SSH utility, such as cluster SSH, to run node tool snapshot on each node in the cluster. That's equivalent to making a full data backup. Taking a global snapshot is one best practice before an upgrade. To configure snapshot, 2 parameters can be set in cassandra.yaml. First, auto snapshot. Enabled by default, it automatically takes snapshot of the data before keyspace truncation or dropping of table. Another one is snapshot before compaction, disabled by default. It automatically takes snapshot before compaction and is useful when there is a data format change. Note that it doesn't automatically clean up older snapshots. As old snapshots are not automatically cleaned up by Cassandra, we need to manually remove them using node tool clear snapshot command. We may specify the keyspace and snapshot to be removed. If no parameter is given, all existing snapshot files for a node will be removed. It's useful to include clear snapshot in data backup process to clear old snapshots before taking a new one. Similarly, use the third-party SSH utility to run node tool clear snapshot to remove snapshots in an entire cluster. Okay, let's continue our demonstration. In CQLSH, insert records into table T. A,1, B,2. Let's check table T's data directory in cluster SSH. Nothing is found there because the data in memtable is not flushed to SS table. Run node tool flush in the nodes and check again. Now SS tables are produced in node 0 and node 1, but not node 2. Remember that we've set the replication factor to 2 only. Insert another record, C,3. In cluster SSH, run node tool snapshot BK without node tool flush. Snapshots are taken on each node. A snapshots folder is created in which hard links to the data files are created. Look into the snapshots folder. Subdirectory with the name of a timestamp exists in each node. They are slightly different from each other, implying inconsistency may exist. In node 0, change to the subdirectory. Hard links to the data files are found there, and we see that 2 SS tables are in node 1 now. Data was flushed before a snapshot is taken. Insert one more record, D,4. Take snapshot again. Now there are 2 snapshots in the folder. Let's clear the earliest snapshot by node tool clear snapshot command. We need to specify the snapshot to be removed in each node. Check the snapshots folder. Now only one snapshot is retained. Now you're familiar with snapshot, its mechanism and configuration. You also know that taking and housekeeping snapshot is easy and understand how snapshots are stored. Next, we're going to look at another closely related topic, incremental backup. In this video, I'm going to introduce incremental backup in Cassandra. It's natively provided by Cassandra for making incremental data backup and must work with full snapshot. I'll explain its mechanism and the available configuration options. Then I'll demonstrate how incremental backup works in a cluster. Comments on more advanced backup tools are also included for your reference. By default, incremental backup is disabled. When it is enabled, Cassandra will create hard link to each on-disk SS table in a Backups folder under the Keyspace Data folder. Contrasting to Snapshot, incremental backup allows storing backups off-site without transferring entire snapshots, and thus saving both network bandwidth and disk space. The same node tool snapshot command is used to make incremental backup. It should be enabled on each node after a cluster-wide snapshot is performed, as illustrated on the diagram. Incremental backup only backs up data updated since the last snapshot was taken. Cassandra creates a hard link to each SS table flushed or streamed locally in a Backups subdirectory of the Keyspace data. Note that housekeeping those hard links is the administrator's responsibility. When combined with snapshots, it provides a dependable, up-to-date backup mechanism. To enable incremental backup, we need to set the parameter incremental backups in Cassandra.yaml to true. I'll show you how to do it in the following demonstration. In this demonstration, I'll enable and make 2 incremental backups and walk you through the directory structure. Exit CQLSH. As a full snapshot has already been taken in the previous video, it's not required here. Now, enable incremental backup. Stop the cluster. Edit Cassandra.yaml in all nodes. Change the incremental backups parameter to true. Save and exit. Start the cluster. Open CQLSH again. Use BK keyspace. Insert 2 more records. E,5, F,6. All right. Take snapshot. A new folder is created in Snapshots folder in each node. Let's check Table T's data directory. A new folder called Backups is found in each node. Look into it. There are hard links to some SS tables, but not all of them. Only new SS tables that were generated since the last full snapshot are linked in Backups directory. Therefore, each time snapshot is taken, all SS tables are hard linked in a new snapshot directory that will consume disk space. For incremental snapshots, only new SS tables are hard linked, and thus saving much disk space. When the size of the data in the cluster grows, the administrator needs to monitor and manage the disk space usage on each node more carefully. Frequent housekeeping of the hard links may help, but it's labor-intensive. As shown in the previous videos, the native backup tools provided by Cassandra are rather primitive and manual, only suitable for a small-scale cluster. When the size of the cluster or the size of the data in the cluster grows, more advanced backup tools will be required to simplify the manual steps of the routine backup tasks. The need to automate the backup process and schedule it on a regular basis to make consistent full snapshots for each node in the cluster is obvious. The hard links are created locally, which doesn't account for any potential problems with the local disk. We may need to make real copies of snapshot and backup files and put them on off-site storage. In addition, Cassandra only retains one set of incremental backup, which limits the flexibility of retaining incremental backups for previous snapshots. Some Cassandra users have made solutions to tackle these problems. You may visit the provided URLs for further references. Now you're familiar with incremental backup, its mechanism and configuration. With full snapshot and incremental backup combined together, an effective and efficient backup strategy can be made. Next, we're going to look into the commit log and how it provides data durability in Cassandra. In this video, we'll look into the details of the commit log of Cassandra. It's an internal archive log mechanism to assure data durability and provide auto-recovery when a node fails. I'll explain the auto-recovery mechanism provided by commit log and introduce its two configurable modes of operations and comment on their uses. At the end, a demonstration will wrap up this video. Commit log is the first place where Cassandra writes data on disk to ensure durable writes before acknowledging the client application. Every write that the client receives a successful response for is guaranteed to be written to the commit log. Then the write is made to the current mem table that will eventually be flushed to on-disk SS table when large enough. After that, the data in the commit log is purged. In the event of a node failure, Cassandra replays the commit log to rebuild mem table on service startup. As shown in the previous videos, node tool flush can be run manually to produce a new SS table and delete the commit logs referring to the data in the corresponding mem tables flushed. The location of commit log can be configured by the commit log directory parameter in cassandra.yaml. The default is in the commit log directory under Cassandra's data directory. For performance reasons, commit log isn't immediately synced to disk by default. This synchronization behavior can be configured by the commit log sync parameter, also in cassandra.yaml. Two sync modes are provided. First, the default, periodic mode. Cassandra acknowledges writes to the client immediately and syncs the commit log to disk in regular intervals, specified by commit log sync period in milliseconds parameter, every 10 seconds by default. It means there is a risk of losing up to 10 seconds of writes if the node fails. However, this risk is mitigated by a replication factor of bigger than 1, assuming that the chance of more than one node failing at the same 10 seconds is very low. The other one is batch mode. It doesn't acknowledge writes to the client until the commit log has been synced to disk by batch. The duration of the batch window is set by commit log sync batch window in milliseconds parameter. It's the safest mode, but may significantly increase write latency and decrease the system throughput. Use this mode only when absolutely necessary. Here I'll simulate a node failure by killing the Cassandra process and examine auto recovery after service startup. In CQLSH, insert a new record. In cluster SSH, type in the command to kill the Cassandra processes to simulate node failures. As such, the record just inserted hasn't been flushed to SS table. Back to CQLSH. Select star from T. An error message, tsocket red 0 bytes, comes out that shows the cluster is down. Now start the cluster again. Reopen CQLSH. Use BK keyspace. Query the content of table T. All records are there, showing that auto recovery was successful. Now you understand how commit log works in Cassandra to ensure durable writes and auto recovery, and how to choose the appropriate sync mode to meet the needs. Next, we're going to perform point-in-time recovery through its provided manual procedures. In this video, I'm going to introduce the various restore and recovery methods of Cassandra. I'll explain the point-in-time recovery feature and different types of restore methods. Also, a demonstration of the complete point-in-time recovery procedure will be given to summarize this section. In previous sections, you've known that snapshots and incremental backups are merely hard links or copies of the SS tables. When we recover the data either because of a node failure or in need of rolling back data intentionally, all SS tables in the required snapshots and backups have to be present as they existed at that point in time. As shown on the diagram, a full snapshot is a must if incremental backup is involved. Cassandra supports several methods of restoring snapshots. Method 1, the SS tables in the snapshot files can be imported into Cassandra by SS Table Loader. Method 2 is copy the snapshot SS tables into the data directory and use JMX mbean to load SS tables by calling load new SS tables operation in JConsole. Node tool refresh may also be used instead. Method 3 is use node restart method. It must be performed offline, meaning that all nodes involved must be shut down during the recovery. Then copy the snapshot SS tables into the data directory and start the relevant nodes again. Beware that this is a CPU and I/O intensive activity. Let's look step by step into the node restart method of point-in-time recovery. Step 1, shut down the affected nodes. Step 2, remove all commit log files. Otherwise, Cassandra's auto recovery feature may replay the writes in commit log on top of the point-in-time data, leading to data inconsistency. Step 3, remove all data files in the affected data directory, but retain the snapshots and backups subdirectories. Step 4, locate the desired snapshot folder. Step 5, copy the files in the snapshot folder into the data directory. Step 6, if incremental backup is enabled, also copy the files in the backups folder into the data directory. Step 7, repeat steps 3 to 6 for each key space in turn. And step 8, finally, restart the nodes. In cluster SSH, shut down Cassandra. Go to commit log directory and delete all files there. Then delete all files in table T's data directory. Assuming that I want to recover to the earliest snapshot. In node 0, copy all DB and text files from the snapshot directory into table T's data directory. Applying the same steps in node 1 and node 2 respectively. OK, start Cassandra. Reconnect CQLSH. Check the contents of table T. Only 4 records are shown, 100% correct. We've successfully turned back the clock. Now you've learned about several restore methods and how to perform point-in-time recovery on Cassandra. In this section, the various backup and recovery options provided by Cassandra have been introduced with demonstration. Full backup, incremental backup, auto recovery, and point-in-time recovery are important features for a production system. Now you should be able to protect your precious data properly. One major drawback is that backup and recovery usually involve a lot of manual procedures unless you develop scripts or choose the commercial editions. I think this situation would be improved in future releases. In the next section, we'll look for different ways to discover potential bottleneck in the cluster and boost up Cassandra's performance. In this video, I'm going to talk about storage strategies and some basic OS tuning for Cassandra. Cassandra is basically a fat client design, meaning that its physical storage is distributed with each node of the cluster. I'll highlight the most typical measures in physical storage design and OS for high performance. First, let's look into the storage strategies for Cassandra. You know that Cassandra's storage architecture is very simple and is classified into commit log and SS tables based on the different I/O behaviors. It's wise to have dedicated hard drives for commit log and SS tables respectively. A dedicated commit log disk is very suitable for frequent write workloads. Its size need not be large, as each commit log should be quite small in size. But the disk should be fast enough to receive all of writes as appends, that is, sequential I/O. SATA disks are fine, and solid-state drives, of course, perform much better. Traditionally, a common design technique known as redundant array of inexpensive disks, or RAID, is used to provide fault tolerance and performance improvements on disk storage. In fact, RAID is optional, since Cassandra has a brilliant built-in fault-tolerant architecture by design. As the size of the cluster increases, the usefulness of RAID diminishes, so it's only suitable for small clusters. There are many RAID levels, but for Cassandra, the following 3 may be considered. First, RAID 1, also known as mirroring, requires at least 2 disks for fault tolerance and is appropriate for commit logs. Second, RAID 0, also called striping, requires at least 2 disks, but doesn't provide fault tolerance.
It's suitable for SS tables and is the fastest option for reads and writes. When a disk failure occurs, data is recovered via Cassandra's built-in repair mechanism. Then, RAID 10, suitable for SS tables but requires at least 4 disks. It has the advantage of avoiding large repair operations, as in the case of RAID 0. Alright, let's move to OS tuning. I'll cover 3 basic OS tuning measures here. First, the recommended file system for Cassandra is ext4. That is provided as default by most of the updated Linux distributions. ext4 is a journaling file system that keeps track of the changes to be made in a journal before committing them to the file system. Another choice is XFS. It combines advanced journaling technology with full 64-bit addressing and scalable structures and algorithms that deliver a scalable, high-performance file system. ext4 performs better than XFS on small clusters. However, ext4 gets a lot worse when the cluster grows up. So, if you require a large-scale deployment and have enough resources, XFS can provide better performance gain. Then, disable swap memory. OS may sometimes decide to swap parts of memory to disks, called pages. Reading those pages on disk takes much longer time than reading in memory, which leads to unpredictable performance. We may turn off all swap memory in the system by executing the swap off command and editing the /etc/fs tab to ensure swap not reactivated on OS startup. If the OS isn't dedicated to Cassandra, we may use JNA to lock in memory such that the OS doesn't swap out Cassandra's JVM and hence avoids related performance issues. When JNA is enabled, we may check /proc/meminfo to see if a portion of memory is unevictable. Lastly, enable memory mapped I/O. It may help Cassandra perform better than standard I/O in some cases. It requires 64-bit OS to fully leverage the benefits, and is configured by setting disk access mode parameter to mmap in cassandra.yaml. Be sure to run tests to evaluate the performance improvements. Okay, let's see how to deal with swap settings and prove that JNA locks in memory for Cassandra. Look inside /etc/fs tab. It stores the static file system information. It's the root mount point of ext4 file system. 2 lines below that, it shows the swap file system doesn't have an associated mount point, as specified by none. Another way to check is /proc/swaps. No entry is found there, meaning that swap is off in the system now. For process-specific swap, type in sudo grep unevictable /proc/meminfo. Unevictable is 0 kilobyte, so process-specific swap is off. Check Cassandra status. It's not running. Start it and check meminfo again. This time unevictable is not 0. Some processes have locked a piece of memory as swap. Double-check Cassandra status. It's running. As mentioned, JNA is required to enable process-specific swap in Cassandra. Let me prove it to you now. Stop Cassandra. Change to Cassandra's library directory. JNA jar library is there. Rename that jar library to some other name so that Cassandra won't load it on startup. Start Cassandra. It's running. grep unevictable again. 0 kilobyte is found. It proved that JNA locks in memory for Cassandra process. Now you know how to plan the hard drives, the file system, and some tuning opportunities on the OS. You also know that JNA provides a fine-grained control on swap memory. Next, we're going to dive into the Java virtual machine and its garbage collection. In this video, I'm going to introduce how to tune Java resources to achieve higher performance and responsiveness. I'll recommend JVM configuration for good performance, and the important things about tuning the Java heap and garbage collection. A good JVM should support 64-bit architecture, low-pause garbage collection, memory-mapped file, and Java native access, respectively. The central place to tweak the JVM settings for Cassandra is cassandra-env.sh. The default values provided inside are a good starting point, and detailed remarks are given to each parameter, so I suggest you taking some time to read through all the remarks. Here I highlight 2 quick and simple tuning options for you. First, disable assertion. All you need to do is remove -ea from the JVM opts variable. Second, applicable in 64-bit JVMs, enable compressed references by setting the Used Compress Ops option. Be careful that different JVMs have different behaviors, and you need to test run each tuning modification to verify the effectiveness. For this course, I've been using Oracle Hotspot JVM version 6. Two major factors have profound impacts on JVM performance are the Java heap and garbage collection, GC. Let's talk about the heap first. Because Cassandra spends significant amounts of time interacting with I/O infrastructure of the system through JVM, a well-tuned Java heap size is very important. In general, larger heap results in better performance. However, it's not always the case. For example, Java 6 can only gracefully handle GC below a heap of 8 GB. Once the heap size exceeds this limit, the handling will deteriorate quickly in most cases. It'll also leave insufficient OS page cache for frequently accessed data. So the rule of thumb is keep Java heaps small relatively, and give more memory for OS page cache. Heap configuration is done in Cassandra-env.sh. It automatically determines a heap size by a user-defined function, calculate heap sizes. Or you may set the values of two variables, max heap size and heap new size, for further customization. They are usually modified together to control the heap size. Max heap size is used to specify the maximum heap size, that is -xmx and -xms options for the JVM. Keeping the minimum heap size equals to maximum heap size locks in memory at process start and keeps it from being swapped out by the OS. The guideline from Cassandra is to allocate half of the memory when the physical memory is under 2 GB. 1 GB is assigned when the physical memory is between 2 and 4 GB, and 25% of the memory when the physical memory is above 4 GB. Another variable is heap new size. It's the size of the young generation, equivalent to the -xmn option. The larger it is, the longer the GC pauses, so be very careful. The sizing guideline is 100 MB times the number of physical CPU cores. JVM pause, or GC pause, is occasional pause in JVM operations due to periodic allocations or deallocations of runtime Java objects with a large heap. It works concurrently with the running application to reclaim memory with a few pauses only. This mechanism is called concurrent mark sweep, CMS. The most popular CMS settings can be set in the JVM opts variable, as shown on the screen. Another mechanism is parallel young generation collector, PYGC. It causes GC to happen in parallel using multiple CPUs so as to decrease GC overhead and increase application throughput. PYGC is also enabled in the JVM opts variable, as shown on the screen. Okay, let's have a quick overview of the Cassandra-env.sh file. Change directory to /etc/Cassandra. Open Cassandra-env.sh. You see the calculate heap sizes function is here. Look down further. We found max heap size and heap new size. Keep going. Almost at the bottom of the file, a bunch of GC tuning options is shown. It shows that CMS and PYGC have already been enabled. Now you're familiar with the two most important aspects of JVM, some of its tuning options and configuration parameters. Next, we're going to focus on different types of cache and see how it can be made use of to improve performance on Cassandra. In this video, I'm going to elaborate on Cassandra's caching mechanism and the corresponding tuning strategies. Cassandra has different caches to boost up performance for read and write operations respectively. I'll also introduce the commonly used configuration parameters for tuning caches. First, cache for read performance. It's integrated with the database in each node and is automatically distributed across the cluster, so no separate caching layer is required. The main advantage is that the cached data is consistent with the on-disk data in database. It also avoids the cold start cache problem. Cassandra provides key cache and row cache for data retrieval. Although both of them can improve read performance, either one is enabled for a table in most cases. An exception is archive table, for which the caches should be disabled entirely. Here are some tips for efficient cache use. First, store lower demand data or data with extremely long rows in a table with minimal or no caching. Second, deploy a large number of nodes under a relatively light load per node. And finally, logically separate heavily read data into separate tables. Let's drill down a bit about key cache and row cache. Key cache is a cache of primary key index, and therefore a large number of keys can be cached without using much memory. It can save CPU time and memory when compared to OS page cache. When only key cache is enabled, further disk or OS page cache activities are required to read the row of data. Then, row cache. It's a cache of holding the entire row in memory when a row is accessed, such that further reads against that row wouldn't involve disk activities. So it allows a high rate of low latency reads. A special kind of row cache is called off-heap row cache. It stores cached rows in native memory outside of the Java heap, leading to smaller per-row memory footprint and reduced heap requirements. To enjoy this feature, JNA is required. Now let's turn to the cache for write performance. It's also built in by design. During write operations, memtable is used for buffering and sorting data in memory before flushing to disk as an SS table, resembling a write-back cache. Note that write-back cache is a caching method in which modifications to data in the cache are not copied to the cache source until absolutely necessary. It improves performance because a write to the high-speed cache is faster than to disk. So how frequent the flush occurs has impact on write performance. The memtable throughput can be increased when the write load includes a high volume of updates on a smaller set of data, or a steady stream of continuous writes occurs. It really depends on data pattern and write load. In general, a larger memtable leads to less often flushes but requires more Java heap memory. Allocating more memory for memtables reduces the memory available for read caches and other internal Cassandra structures. Since memtable is a per-table setting, the number of table on a node also has influence. The main cache and memtable configuration parameters can be modified in Cassandra.yaml. It's effective for one node only, and you need to apply the modification to all nodes to have a consistent caching behavior across the cluster. Otherwise, unpredictable performance issues may arise. Cluster SSH or parallel SSH may help in changing the Cassandra.yaml files on all nodes simultaneously. Let's go through some parameters. First, saved caches directory, the location of saved caches. Key cache size in megabytes and row cache size in megabytes are the capacity of all key caches and row caches on the node. Similarly, key cache save period and row cache save period control how often to save the key caches and row caches to disk. Then, row cache provider. It's the implementation you can choose for row caches on the node. The remaining three are related to memtable. Memtable total space in megabytes is the total memory used for all memtables. Memtable flush writers is the number of memtable flush writer threads. Lastly, memtable flush queue size is the number of full memtables to allow, pending flush. You may also use CQL to set table cache to optimize the use of cache memory without manual tuning. The options are keys only, which is the default value, rows only, all, and none. Let's have a look at how to set table cache in CQLSH. Open CQLSH, use quote keyspace, describe table FB3. The caching is keys only. Now change it to all using alter table command. Describe FB3 again, the caching is changed to all. Now you're familiar with read and write caches of Cassandra and know how to modify the settings. Next, we're going to take a look at other performance tuning opportunities related to SS table, particularly for compaction and compression. In this video, I'm going to introduce the compaction and compression of SS table. Consolidating SS tables and configuring compression of tables can improve performance. Cassandra also provides write survey mode to test compaction and compression performance. Let's cover compaction first. Compaction is performed to free up disk space by merging large accumulated SS tables. It merges data and keys, combines columns, discards tombstones, and creates a new index to form a new SS table. It's intended as a transparent background operation to improve performance by reducing the number of required disk seeks. We may use CQL to fine-tune compaction on a table with the syntax as shown. During compaction, a temporary spike in disk space usage and disk I/O activity may have negative impact on performance. When tuning compaction on a table, we need to choose a suitable compaction strategy. Two choices. Size-tiered compaction strategy, the default, triggers a minor compaction whenever there are a number of similar-sized SS tables on disk, as configured by the min threshold parameter. It causes bursts in I/O activity and thus negatively impacting on read performance. And it can temporarily double the size of SS tables for a table during compaction. Size-tiered compaction is good for write-heavy workloads, write-once rows, and when the cluster is already pressed for I/O. Another choice is leveled compaction strategy. It creates SS tables of a fixed, relatively small size, as configured by the SS table size in megabytes parameter, and groups the SS tables into levels. It spends more I/O on compaction in order to guarantee non-overlapping SS tables within each level. And each level is 10 times as large as the previous level. The main advantage is a more uniform and predictable disk I/O pattern. Typically, a row can be read from a single SS table 90% of the time. Moreover, row keys are merged into non-overlapping SS tables at each level, leading to improved read performance. Leveled compaction is good for low-latency read workloads, workloads of high read-write ratio, and frequently updated rows. A related compaction parameter, tombstone compaction interval, is configured in Cassandra.yaml. It's the minimum time to wait after an SS table creation time before considering it for tombstone compaction. Next, compression. Enabled by default, it maximizes storage capacity by reducing the volume of data on disk and disk I/O activities. It's suitable for read-intensive tables containing many rows having the same columns. It can quickly locate the rows in SS table index and decompress the relevant row chunks. It doesn't have negative impact on write performance as it compresses SS tables only once when written to disk. CQL is used to set compression on a table with the syntax on the screen. Cassandra provides 3 compression algorithms, or compressors, to meet your compression needs. The default is Snappy Compressor, based on Google's fast, snappy compression-decompression algorithms, and is recommended for read-heavy workloads. Second, Deflate Compressor. It's a Java zip implementation offering a better compression ratio and thus good for disk space savings. And the new LZ4 compressor since Cassandra version 1.2.2. It's a very fast, lossless compression algorithm about 50% faster than Snappy. It's also good for high read performance workloads. The default compressor is configured in Cassandra.yaml through the SS table compression parameter. To test compaction and compression performance, we may make use of the write survey mode. It's a node startup option for benchmarking the write performance differences without affecting the whole cluster. Set the JVM opts variable in Cassandra-env.sh to enable write survey mode as shown. When enabled, a node is added to a cluster and accepts all write traffic as if it were part of the cluster, but not officially joining the ring. Then we can use stress testing tools such as Cassandra Stress, that will be introduced in the next video, to benchmark the compaction and compression performance with live data. Okay, let's see a demonstration. Open CQLSH, use quote keyspace, describe FB3. Here are the compaction and compression settings. Use alter table statement to change the compaction strategy to leveled compaction strategy, and the SS table size to 10 MB. Also change the compressor to deflate compressor with a chunk size of 128 KB. Describe FB3 again. Done. Now enable the write survey mode. Stop Cassandra. Change directory to /etc/Cassandra. Make a backup of Cassandra-env.sh. Edit the file. Go to the bottom, append the line of JVM opts as shown on the screen. Save and exit. Start Cassandra. Change to Cassandra's log directory. Check system.log. Jump to the bottom. A line there says startup complete, but write survey mode is active, not becoming an active ring member. We're successful to turn on the write survey mode for performance tests. Now you're familiar with compaction and compression and how to enable the right survey mode to test out their performance. Next, we're going to finish this section by introducing the stress testing tool provided by Cassandra and how to trace CQL requests. In this video, I'm going to introduce the stress testing tool bundled with Cassandra and how to trace CQL requests. I'll present the usage of the stress testing tool and the request tracing feature, followed by a short demonstration. Cassandra provides a utility called Cassandra Stress for stress testing. It can generate different workloads according to the given options. It's basically a shell script wrapping a Java program in stress.jar library. During its execution, Cassandra Stress reports performance data periodically about its running tests, including the total number of operations since the start of the test, the number of operations performed during the interval 10 seconds by default, the number of keys or rows read or written during the interval, the average, the 95th percentile, and the 99th percentile latency for each operation during the interval, and the number of seconds elapsed since the beginning of the test. Here are the typical options to run stress testing. -D provides the host nodes to run the stress test, -N is the number of keys, and -O is the operation to perform, which can be insert, read, and so on. Cassandra Stress automatically creates a default keyspace and several column families for its test data. Be sure to run several rounds of the test to get more stable performance metrics. Request tracing is a new feature since version 1.2. It's helpful in understanding the internal operations of processing a CQL statement and is very useful in troubleshooting. It can be run on an ad hoc basis. Moreover, enabling or disabling tracing is very simple in CQLSH with the tracing command. When enabled, request tracing outputs a description of each internal step along with what nodes are affected, time per step, and total time of request. Those variable tracing information are temporarily kept in two tables, sessions and events, in the system traces keyspace for 24 hours. You need to copy them to another location manually to preserve them. Let's see a demonstration of stress testing and request tracing. Type in Cassandra Stress. As a simple demonstration, I use the default values, that is, inserting 1 million rows at the local node. The keyspace for test data is created. After 10 seconds, a line is reported. The first column says that 21,700 rows are inserted, then 2,170 operations, and hence 2,170 rows are written during the interval. Next, the average, 95th, and 99th percentile latency for each insert during the interval are 13.4, 53.5, and 305.8 milliseconds respectively. And the last column simply says that 10 seconds are elapsed. More lines are reported periodically. After a while, the test is finished and we get the final figures. Conversely, we can run stress test on read performance. Also use the defaults, type in Cassandra Stress-O read. Performance figures are reported in the same format and their interpretations are the same as well. Check the test data keyspace folder, change to superuser. Change directory to /var/lib/Cassandra, then data and keyspace 1. 5 column families are there. Check the disk usage by du command. The test data occupies more than 290 megabyte of disk space. Now move on to request tracing. Open CQLSH, use quote keyspace, enable request tracing by typing tracing on, test it by selecting all rows of FB3. The rows are shown, and after that a tracing session is shown with an ID and a profile of the internal steps of processing the query. The leftmost column is the activity description, then its timestamp and the node that did the activity, and finally the elapsed time. So we get a profile of the query. Disable request tracing by the tracing off command. Now you've learned about the stress testing tool and request tracing to facilitate performance tuning on Cassandra. In this section, basic performance tuning measures have been introduced with brief demonstrations. Actually, performance tuning is a very complicated ongoing exercise and requires iterative executions and testing to collect metrics for analysis. When combined with Section 4, Setup Monitoring, potential bottlenecks can be discovered and appropriate performance tuning measures can be tested and tried. It's an empirical process. You're always recommended to refer to the updated official documentation for further details. In the next section, I'll provide supplementary information and wrap up the entire course with closing remarks. In this section, we'll cover some supplementary information, for example, repairing nodes, scaling in and out, cloning virtual machines, cluster SSH, and closing remarks. In this first video, I'm going to introduce how to repair nodes in a Cassandra cluster. Hinted handoff ensures high write availability and dramatically improves response consistency after temporary outages, such as network failures. Node repair can ensure data consistency among different nodes in the cluster. However, there are certain things we should pay attention to when doing so. First, let's take a look at hinted handoff. When a write is performed and a replica node for the row is down or does not respond to the request, the coordinator will store a hint locally in the system.hints table. The hint indicates that the write needs to be replayed to the unavailable nodes. After the unavailable node has recovered, the coordinator sends the data row corresponding to each hint to the target. By default, hints are saved for 3 hours after a replica fails, as configured by max hint window in milliseconds in cassandra.yaml. If the replica is down longer than that, it is likely permanently dead. In that case, we need to run a repair to re-replicate the data before the failure occurred. That will also be covered in this video. Okay, let's watch a demonstration on hinted handoff. In cluster SSH, check the status of the 3-node cluster. All nodes are running. Open CQLSH. For testing, we'll create a keyspace called HH and a table called test. Create keyspace HH, use HH keyspace, create table test, insert a record, check the record. Alright. Now we need to check the nodes that hold the record. Use node tool getEndpoints command as shown. The record is on node 0 and node 1. Then we shut down Cassandra service on node 1 to simulate a temporary failure. Check cluster status. Node 1 is down. Go back to CQLSH. Update the record to fire a write request. Check the record. Cassandra accepted the write request. Now restart Cassandra service on node 1. Check cluster status. Okay, all up. Go to Cassandra log directory. View system.log. Go to the bottom. It shows that hinted handoff operations was automatically done on node 1. Now let's move on to routine node repair. Data inconsistency may arise in a Cassandra cluster over time. There is a need to repair those data inconsistencies across all of the replicas for a given range of data. It's also known as anti-entropy repair. Typically, we need to run repair when, first, during normal operation as part of regular scheduled cluster maintenance, unless Cassandra doesn't delete data, or during node recovery, when bringing a node back into the cluster after a failure. The third situation is on nodes containing data that is not read frequently. And lastly, to update data on a node that has been down for some time. We use node tool repair with the syntax as shown on the screen to repair a keyspace or a table. We may run node tool repair with PR option, such that only the first range returned by the partitioner for a node is repaired, and each node in the cluster is repaired in succession without duplicating work. It's the preferred choice. Without PR option, all replica ranges that the node is responsible for are repaired. Here are some guidelines of repairing nodes. First, the hard requirement for repair frequency is the value of GC grace seconds, 10 days by default. We should run a repair operation at least once on each node within this time period. It ensures that deletes are properly handled in the cluster. Otherwise, you may have risk of forgotten deletes. Please refer to the URLs below to have the full details of forgotten deletes. Next, repair requires heavy disk and CPU consumption. Therefore, use it with caution when running node repair on more than one node at a time. We should schedule regular repair operations for low usage hours. If the disk storage on nodes grows significantly, use node tool compact to remove duplicate data that resulted from the repair. Then, in systems that seldom delete or overwrite data, Raise the value of GC grace seconds with minimal impact to disk space. Obviously, it means that the node repair operations can be run less frequently, and thus allows wider intervals for scheduling repair operations with the node tool utility. Okay, let's have a look at how to run node repair. In a terminal, check the cluster status. All nodes are up and running. I'm going to repair the BK keyspace. Type in node tool repair BK. Repair is starting and shall take a while. A list of the range repaired is then shown, and a message states that the repair has been finished. Now you know hinted handoff and how to repair data inconsistency by using node tool repair. It should be run not only in failures, but also on a regular scheduled basis. Next, we're going to see how to scale the cluster by removing and adding nodes. In this video, I'm going to describe how to scale a Cassandra cluster by removing and adding nodes into it. I'll walk you through removing a failed node, decommissioning a running node, virtual node, adding a node to an existing cluster, and replacing a dead node with short demonstrations. For a failed node, Cassandra doesn't assume it lost forever, since temporary failure of a node is very common in a distributed environment. The other nodes in the cluster become aware that node failure through the gossip protocol. They will store hinted handoff messages and will attempt to redeliver the hinted messages when they detect the failed destination node is up again. However, if the node is lost forever, it's the administrator's responsibility to actively acknowledge the failure using the node tool remove node command. Node tool remove node can only be run on a node in the down state. By design, each keyspace has a configurable replication factor, so that when a node is removed, Cassandra will begin actively replicating the missing data until it is all stored on the number of nodes specified by the replication factor. Okay, let me simulate a node failure and remove it from the cluster. Here I use cluster SSH. Check Cassandra's status. All nodes are up and running. Now I shut down node 2 to simulate a node failure. Open a new terminal. Check status again. Node 2 is now in the down state. Copy the host ID. Type in node tool remove node, paste the host ID, and press Enter key. Check node tool status. Node 2 is now not only in the down state, but also in the leaving state, meaning that node 2 is leaving the cluster. After a while, check node tool status again. Only 2 nodes are left sharing the load, and node 2 vanished. Remove node operation is also finished. Decommissioning a node is different from removing a node, in that it's a process for which a node in the up state is removed. It's executed by the node tool decommission command. It's more efficient than remove node, because the node leaving the cluster helps calculate and transmit the data that will need to be moved to other nodes before leaving. But it can take a long time to complete, depending on the amount of data in the cluster. The node first anti-compacts the data it has, and then streams the data to the node that will now be responsible for that data. We may use the node tool ring command to monitor the progress over time. The decommissioned host will eventually vanish from the list. I'll demonstrate how to decommission a node as follows. In cluster SSH, run node tool status. All nodes are up and running. This time I decommission node 2. In node 2's terminal, type in node tool decommission. Switch to node 0's terminal, check status. Node 2 is up and leaving. After a while, decommission is finished. Check status again. Only node 0 and node 1 are up and running. Node 2 vanished. Remember that token is used to mark the ownership range of row keys in a node. Before Cassandra 1.2, each node is assigned a single token, and hence, each node owns exactly one contiguous range in the ring space. Since version 1.2, virtual node, also called vnode, was introduced to allow many tokens per node. The default value is 250 vnodes per server. vNodes can be randomly selected and be non-contiguous within a cluster, providing better distribution of load, faster rebuild and repair, greater reliability, and simpler operations. vNodes greatly simplify adding nodes to an existing cluster. It's the recommended approach. Now we don't need to calculate and assign tokens to each node. We also don't need to rebalance a cluster, because a node joining the cluster assumes equal responsibility for an even portion of the data. The high-level steps of adding nodes are: first, install Cassandra on the new nodes, but don't start Cassandra. Then, configure settings in cassandra.yaml and cassandra-topology.properties configuration files, if applicable. Next, start Cassandra on each node 2 minutes after the last node started. After all new nodes are running, run node tool cleanup on each of the previously existing nodes in turn. Non-vnode. It's similar to adding vnode to an existing cluster, except that we need to recalculate and generate new tokens for the existing and the new nodes of the cluster, as well as rebalancing the cluster. You may refer to the given URL for further information. Replacing a dead node is simply a combination of adding a new node and removing the failed node. First, confirm that the node is dead by running node tool status. Then add and start the replacement node. Finally, remove the dead node from the cluster using the node tool remove node force command. Pretty straightforward. Now you're familiar with how to remove a failed node and how to decommission a running node. You also know more about virtual nodes and how to add new nodes to a cluster and replace a dead node. Next, I'm going to give you supplementary information on how to clone virtual machines. In this video, I'm going to prepare a virtual machine as a seed node for cloning 2 more VMs to form a Cassandra cluster. I'll make use of the clone feature provided by VMware Workstation to do the task. Other similar virtual machine management software, such as VirtualBox, also provides such clone feature. I'll highlight the major steps of cloning VM in VirtualBox, however, you may consult its documentation for further details. In virtual machines terminology, a clone is a separate copy of an existing VM, or the parent, with unique MAC address and UUID. The major advantage is to save time and effort in repeatedly installing a guest OS and applications on every similar VM. With clones, many copies of a VM can be made from a single installation and configuration process. Thus, it's useful when many identical virtual machines must be deployed to a group. For example, building a Cassandra cluster. It's supported by most virtual machine management software, and I'll use VMware Workstation for demonstration. In the following demonstration, I'll configure a seed Cassandra node before using it as the parent for cloning 2 more nodes. Then I'll also configure the virtual network to be used by the cluster. We're now in the seed node, in which a single node Cassandra has been set up and configured. First, I'll disable the auto start of the Cassandra service. Check Cassandra status. Shut it down by sudo service cassandra stop. Remove all existing data in Cassandra's data directory. Disable autostart of Cassandra by sudo update rc.d cassandra disable. OK. Then I'll configure the network properties. Get the IP address by ifconfig. Copy the IP address and then add it to hosts file. Add a new line. For example, in this demo VM, 192.168.0.143 node 0. Save and exit. Change the default hostname Ubuntu to node 0 in /etc/hostname file. Shut down the VM. I can now clone the virtual machines. In VMware Workstation, select UBTC00, which is the parent, on the left menu. Then right-click and select Manage, Clone. The Clone Virtual Machine wizard comes out. Click Next. Select the current state in the virtual machine and click Next. Select Create a linked clone and click Next. Change virtual machine name to UBTC01 and click Finish. When the cloning process is finished, click Close. Repeat the above steps for another VM, UBTC02. On the left menu, select UBTC00 and click Power on the virtual machine. Power on UBTC01 and UBTC02 as well. Log on to the virtual machines. Now I'm going to set up the cluster network. Get the IP addresses and change the host names of UBTC01 and UBTC02 respectively. UBTC01's hostname is node 1, and UBTC02's is node 2. Moreover, this time, I need to add the IP address to hostname mapping of all the nodes in the hosts file. The settings should be similar to the example here. Be sure to reboot UBTC01 and UBTC02 afterwards. Although this course uses VMware exclusively for demonstration, VirtualBox can also do the job exactly the same. VirtualBox adds a clone command since version 4.1.2. The basic steps are: first, close the source VM. Then use VirtualBox Manager to start the cloning process. Next, locate the source VDI file and move the clone to the new location, such as a new host, and create a new VM to use the cloned VDI file. You may refer to the provided URLs for further details. Now you're familiar with how to make a seed node and use virtual machine management software to produce identical nodes by cloning. You also know how to configure the virtual network for the demonstration cluster. Next, we're going to enable passwordless SSH and configure cluster SSH to simplify the management of the Cassandra cluster. In this video, I'm going to set up Secure Shell, SSH, and Cluster SSH to simplify the management of the Cassandra cluster. I'll use public key to enable passwordless SSH login, and will then turn to configure Cluster SSH. By default, SSH requires username and password to log on to remote systems. It becomes burdensome in managing a large Cassandra cluster consisting of tens or even hundreds of nodes. It means you need to repeatedly enter username and password many times. Fortunately, SSH allows automatic login, which is known as passwordless SSH. It uses private and public keys to authenticate the user identity and thus avoids storing plaintext passwords in the system. Let's see how to enable it in the demonstration cluster. In Node 0, generate the private and public keys for SSH by typing SSH keygen. By default, the key will be stored under the user home directory as shown. Press Enter key to accept the default file location, enter and confirm the passphrase, then the key fingerprint and its random art image are shown. First, I'll enable passwordless login on Node 0. Copy the public key to Node 0 itself by SSH copy ID as shown on the screen. Type yes to continue, enter the password, then add identity by SSH add, and test login by SSH Node 0. Great, it works. Exit Node 0's SSH. Repeat the above steps to copy the public key to Node 1, test login to Node 1. Alright. Then Node 2, test login, and done. Cluster SSH is basically a cluster administration tool via SSH. It can control a number of Xterm windows through a single graphical console window, to allow commands to be interactively run on multiple systems over an SSH connection. To install Cluster SSH in Ubuntu, simply enter sudo apt-get install cluster SSH in a terminal. Cluster SSH has both global and user-specific configuration files, and the latter is a more common choice. The user-specific configuration file is stored in the user home directory with the name .csshrc. It can be used to define a cluster as a group of machines to be controlled and customize the behavior of cluster SSH, for example the terminal font, font size, hotkeys, etc. Now I'll demonstrate how to configure it. In a terminal, type in CSSH and press Enter key. The cluster SSH command window comes out. Select File, Exit. Cluster SSH generates its configuration file at its first execution. Edit the configuration file by typing vi.csshrc. Search terminal font size by /font. Change it to 8 by 13 to make bigger the text in the shells. Then scroll to the bottom, append 2 lines. Cluster Cassandra equals node 0, node 1, node 2, and clusters equals cluster Cassandra. Save and exit. Launch cluster SSH again by CSSH node 0, node 1, node 2. Apart from the cluster SSH command window, 3 SSH windows come out, showing that it's connected to node 0, node 1, and node 2 respectively. Since passwordless login is enabled, no questions are asked for password.
Now you know how to set up passwordless SSH and cluster SSH to simplify the administration of a Cassandra cluster. They are indeed very handy and useful in daily operations. Next, I'll wrap up the whole course, introduce some new features of Cassandra 2.0, and provide further references. In this video, I'm going to summarize the course and give you information for further references. In this course, my goal was to give you a good foundation in installing, configuring, administering, and managing Cassandra, so you can use it to build powerful and compelling applications for yourself and for your clients. I've covered why we select Cassandra and its basic theory and mechanisms, data types, data model, and terminologies. I've also installed and configured a single-node Cassandra cluster on Ubuntu, which is then scaled out to a 3-node cluster. I've introduced several topics typical in daily operations, including system monitoring, data migration and indexing, backup and restore, some basic performance tuning techniques, repairing nodes, adding and removing nodes. I've walked you through many demonstrations so you can see how to apply your knowledge to building your own projects in Cassandra. A major new version of Cassandra 2.0 was released in September 2013. It includes many enhancements to CQL, security, and performance. The CQL specification is updated to version 3.1.0. Here are some of the new features and enhancements that deserve your attention. First, lightweight transactions. It allows ensuring operation linearizability similar to the serializable isolation level offered by relational databases, which prevents conflicts during concurrent requests. Then, triggers. It enables pushing performance-critical code close to the data it deals with, and simplifies integration with event-driven frameworks like Storm. And CQL enhancements such as cursors, prepared statement, and improved index support. Eager retries. It avoids query timeouts by sending redundant requests to other replicas if too much time elapses on the original request. And customer thrift server implementation. It's based on LMAX Disruptor, a high-performance inter-thread messaging library that achieves lower message processing latencies and better throughput with flexible buffer allocation strategies. Finally, a list of websites is shown here for your further reference and study. I've also included the program scripts and a command summary card as supplementary materials of this course. I've really enjoyed creating this course for you, and I sincerely hope that it's as useful for you as it has been fun for me.